Welcome to Google Cloud Platform's Advanced CI/CD Techniques and Security Practices. My name is Ron Johnson. In this course, we will describe advanced techniques for managing CI/CD pipelines in GCP, summarize the integration of third-party CI/CD tools like Jenkins and Argo CD within GCP, explain the mitigation strategies for security challenges associated with CI/CD tooling, compare different CI/CD pipeline strategies for multi-cloud and hybrid environments. Identify the role of binary authorization in securing software supply chains. Discuss the implementation of secret management practices in CI/CD pipelines. Describe the application of vulnerability analysis tools in the CI/CD process. Identify IAM policy configurations for different environments within the CI/CD pipelines. Analyze a case study of securing a CI/CD pipeline from code to deployment. Set up and manage CI/CD pipelines for serverless applications on GCP. And finally, we'll explain the best practices for auditing and tracking deployments in GCP. A CI/CD pipeline has various components. Each of these components play a crucial role in creating a robust and efficient CI/CD pipeline. By automating infrastructure provisioning, containerizing applications, thoroughly testing code, monitoring performance, and prioritizing security, you can deliver high-quality software faster and with greater confidence. So let's look at the components of a CI/CD pipeline. So let's first take a look at IAC, otherwise known as Infrastructure as Code. IAC is the practice of managing and provisioning your computer systems, such as servers, networks, databases, using code instead of doing it manually. This makes setup faster, more reliable, and easier to track changes. Some of the key components of IAC would be Terraform. This is a popular tool that lets you write code to describe exactly how you want your infrastructure to be built. Terraform then takes care of creating and managing those resources either in the cloud or on your own servers. GCP Deployment Manager. This is Google Cloud Platform's own tool for doing IAC. It works like Terraform, but specifically designed for managing resources within GCP. And then there's version control. Tools like Git are used to securely track the code you write for your infrastructure. This allows you to see the history of changes. It allows you to collaborate with others. It also allows you to revert to previous versions of the code if needed. And lastly, there's automated provisioning. This is the core idea of IAC. Instead of manually clicking different options to set up servers, you run your code and it automatically creates the infrastructure you need. This is faster and less prone to errors. In short, it helps you facilitate the automated setup and management of infrastructure and application environments. Now let's take a look at containerization and orchestration. Containerization and orchestration are two powerful technologies that work hand in hand to make application management easier and more efficient. Think of them as tools to package, deploy, and scale applications with ease. Some of the benefits of containerization and orchestration would be simplified management. This makes it easier to manage and deploy your applications across different environments, whether it's your laptop, a testing server, or production environment in the cloud. Scalability. An example of scalability would be Cloud Build. This is a service offered by cloud providers such as Google Cloud Platform. It enables you to automatically build container images. This would then allow you to easily scale your application up or down based on demand. Your users would then be ensured a smooth transition experience even during peak traffic times. Automated builds. Containerization enables automated builds of your application, thus ensuring consistency and reliability in your development and deployment processes. That would then mean you can automatically create new versions of your application whenever you make changes to the code. This would then entail reduce the risk of human error and speed up your development cycle. And lastly, integration with GKE. Containers are often used in conjunction with Kubernetes. This is a powerful orchestration platform that makes the deployment and scaling of containerized applications. Google Kubernetes Engine is Google's managed Kubernetes service, which simplifies the process of running Kubernetes in the cloud. This integration makes it easier to deploy, manage, and scale your applications on the Google Cloud platform. Next, let's take a look at automated testing and quality assurance. Automated testing and quality assurance are essential for building reliable and high-quality software. They can help you catch problems early in the development cycle, save time and resources, and deliver a better user experience. So, by automating test execution using cloud-based testing environments and integrating it with a test framework, you can streamline your development process and ensure your code works as expected. Some key aspects of automated testing and quality assurance would be automated test execution. This involves running a suite of pre-written tests automatically when changes are made to the code. These tests check if the code functions correctly and it doesn't break anything that was working before. Saves a lot of time and effort compared to manual testing. Then there's Cloud Test Labs. Cloud Test Labs is a service offered by Google Cloud Platform. It allows you to test your application on a variety of devices and configurations. This ensures that your software works smoothly for different users on things like phones, tablets, and browsers. And lastly, integration with testing framework. Testing frameworks are tools that make it easier to write and run tests. Automated testing systems often integrate with popular frameworks like JUnit for Java or PyTest for Python, allowing you to leverage existing testing tools and libraries. This helps you write tests efficiently and effectively. Another key component of the CI/CD pipeline is monitoring and logging. Monitoring and logging are crucial for maintaining the health and performance of your IT systems. They provide real-time insight into how your applications and infrastructure are functioning, thus enabling you to proactively identify and resolve issues before they escalate into major problems. Some key elements of monitoring and logging include real-time monitoring. Real-time monitoring provides a continuous stream of data, allowing you to see exactly how your systems are performing at any given moment. This enables swift detection and response to anomalies or performance issues, ensuring minimal disruption to your services. Another element is alerts and notifications. Prometheus and Grafana are powerful open source tools that work together to provide comprehensive monitoring and alerting capabilities. Prometheus collects and stores metrics from your systems, whereas Grafana creates intuitive visualizations and dashboards for easy analytics. A third element is metrics collections. By gathering numeric data such as CPU usage, memory consumption, network traffic, and error rates, you can monitor the vital signs of your applications, gaining valuable insight into their overall health and performance. A fourth element is data visualization. Data visualization tools like Grafana transform raw metrics into insightful charts, graphs, and dashboards. This allows you to easily identify trends, patterns, and outliers in your data, making it easier to understand the behaviors of your systems. It also allows you to predict potential issues, thus making informed decisions about optimization. So, by leveraging the power of monitoring and logging and utilizing tools like Prometheus and Grafana, you can gain deep understanding of your IT environment that then empowers you to proactively address problems, optimize performance, and ensure the reliability and availability of your services. The last key component of the CI/CD pipeline we'd like to investigate is security and compliance. Security and compliance are crucial aspects of any organization's cloud infrastructure. They help protect your data, applications, and systems from unauthorized access, theft, and damage. Some key elements of the security and compliance service would be cloud key management. This service allows you to create, manage, and protect the encryption keys that are used to secure your data in the cloud. Using these keys, you can ensure that only authorized individuals or systems are allowed to access your sensitive information and keep it safe from prying eyes. Another element is the Security Command Center. This service provides a comprehensive view of your security posture. It allows you to detect threats, investigate incidences, and manage risk across all your Google Cloud projects. It's like having a security team constantly watching your infrastructure and identifying potential vulnerabilities. It then alerts you about any suspicious activity. Lastly, Vulnerability Monitor. This is like having a team of experts regularly scanning your systems for weaknesses. Vulnerability monitor tools automatically scan your cloud assets, like virtual machines, containers, and applications, for known vulnerabilities and misconfigurations. They help you stay ahead of potential threats and take proactive measures to protect your systems before they can be exploited. So, by implementing these components, you can build a robust security and compliance framework for your cloud infrastructure. This will help you to protect your sensitive data, meet regulatory requirements, and build trust with your customers and partners. Now let's turn our attention to advanced deployment strategies for CI/CD pipelines. Advanced deployment strategies for pipelines go beyond the basics of deploying software and focus on making the deployment process itself smoother, safer, and more efficient. Think of the strategies as tools for refining your delivery process. The components that we'll cover in this section are automated rollbacks, continuous feedback and improvements, hybrid and multi-cloud deployments, and performance optimization. Let's first take a look at automated rollback. The goal of automated rollback is to quickly and safely undo a software update if something goes wrong after its release. It's like having a rewind button for your deployment, helping you to minimize downtime and disruption for your users. Here's how the process typically works. Build and test applications. Before you release new software, you use a tool like Cloud Build to automatically compile your code, run tests, and package your application into a deployable format. Next, you would define your development process. Spinnaker is a continuous delivery platform that helps you automate the process of deploying your application to different environments, such as testing, staging, and production. Next, you would create triggers to revert to a previous version of your application. These triggers could be based on things like monitoring alerts, manual intervention, and lastly, you would revert to a stable version of your application. Once a rollback is triggered, Spinnaker automatically reverts your application to the previous stable version that was working correctly. This happens quickly and seamlessly, minimizing downtime and disruption for users. Next, let's take a look at continuous feedback and improvements. The idea behind this is to constantly make your software development process better. It's like a feedback loop where you're always learning and adjusting, so you can deliver higher quality software more efficiently. Here are some of the concepts and tools that fit into the process. Jira is a project management tool that helps teams track tasks, bugs, and progress. In software development, data issues refer to problems with the information your software uses. BigQuery is a powerful data warehouse service from Google Cloud. It can be used to store and analyze logs, measure performance, and generate reports. In a hybrid or multi-cloud setup, you might be using resources from different cloud providers, such as Google Cloud, AWS, or Azure. Or you could use your own on-premise servers. United management means you can oversee and control all of these different environments from a single place, thus making it easier to track resources, monitor performance, and apply consistent policies. This streamlined approach can save you time and effort, help you avoid the headaches of managing each environment separately. CI/CD helps you automate the process of building, testing, and deploying your software. Having consistent CI/CD practices across different cloud environments means you're using the same tools, workflows, and processes, regardless of where your code runs. This ensures reliability, minimizes errors, and makes it easier to manage changes across your entire infrastructure. It's like having a standardized playbook for software delivery, no matter which cloud platform you're using. Performance optimization is the process of fine-tuning your software to make it run faster, consume less energy, and use resources more efficiently. It's like tuning up your car to get better performance out of it. Streamlining the process of compiling and packaging your software can significantly reduce the time it takes to create a new version. Optimizing your build process involves finding ways to make them faster and more efficient. And instead of reinventing the wheel for every new project, you can create reusable configuration templates for common tasks. Integrating Jenkins with GCP helps you manage the CI/CD pipeline by building, testing, packaging, and deploying the application. It functions as the conductor of your CI/CD process. Jenkins pulls code from your repository, builds your application using tools like Maven, Gradle, or Make, and runs automated tests to ensure your code works as expected. Jenkins packages your application into a deployable artifact, for example, Docker images, jar files, and stores the artifact in GCP's artifact registry. Jenkins triggers deployments to various GCP targets like GKE, Cloud Run, App Engine, or Compute Engine. You can use Jenkins' built-in deployment plugins or custom scripts to interact with GCP's deployment tools. Next, let's take a look at integrating Argo CD with GCP. Argo CD ensures that applications are continuously aligned with the desired state defined in Git repositories, providing automatic synchronization and visualization of the deployment state. Argo CD acts as a stage manager, ensuring your applications are consistently in the desired state. Argo CD follows a GitOps approach, where your desired application state is defined in a Git repository, and it continuously monitors your live environment, comparing it to the desired state in Git. If any differences exist between the live environment and Git repository, Argo CD automatically applies the changes to bring them into sync. This ensures your applications are always running the latest approved version. Argo CD provides a visual representation of your application state and its history, making it easy to see what's happening and troubleshooting any issues. Argo CD easily connects to your GKE cluster or other GCP resources, and can also integrate with Cloud Build or Jenkins for automated deployment triggers. Let's now take a look at an example of Jenkins and Argo CD integration. In the first step, a developer pushes code to a Git repository. Next, Jenkins detects the changes and triggers a build. Jenkins then builds and tests the application. In the fourth step, Jenkins packages the application and stores it in an artifact registry. Jenkins then triggers an Argo CD deployment, and then Argo CD syncs the new image to your GKE cluster. CI/CD pipelines have become the cornerstone of modern software development, enabling faster release cycles and more efficient workflows. However, as these pipelines become more complex and interconnected, they also expose various security vulnerabilities that can be exploited by malicious actors. This slide highlights some of the most common security challenges associated with CI/CD pipelines. In the subsequent slides, we will delve deeper into each of these challenges and discuss potential mitigation strategies to safeguard your software delivery process and protect your valuable assets. Risk of unauthorized code modifications refers to the danger of someone tampering with your source code without your permissions. Injections of a malicious code threat involves the insertion of harmful code into software, often through vulnerabilities and input handling. Code integrity and mitigation of injection attacks includes the implementation of strict access control and authentication. This means putting tight security measures in place to make sure only authorized people and systems can access your code repositories and CI/CD pipelines. Second, you could use code signing to verify code integrity. Code signing is like putting a tamper-proof seal on your code. It adds a digital signature that proves the code hasn't been changed since it was signed. And lastly, you could implement regular code audits and reviews. Even with the best security measures, vulnerabilities can still slip through. Regular code audits and reviews involve having experienced developers or security experts carefully examine your code to look for potential weaknesses or flaws. Another security concern would entail credentials and secret management. In today's complex digital landscape, organizations use a wide variety of credentials and secrets to access different systems and services. The more credentials and secrets you have, the greater the risk of their being accidentally leaked or stolen by malicious actors. Mitigation strategies for protecting credentials and secrets can include services and policies. One such service, Google Cloud Platform Secret Manager, is used to securely store and manage sensitive data like API keys, passwords, and certificates. A policy, for example, could include avoiding hard-coding secrets in repositories. Never directly embed secrets within your source code repository, instead reference them from your secret management system. Another service could be implementing role-based access control. Define and enforce granular permissions to control who can access and manage your secrets. Dependency management can be another area of concern for security. Modern software development often relies on external libraries and components called dependencies. They do so to accelerate development and leverage existing functionality. Some of the risks associated with dependency management include vulnerabilities from third-party libraries, risks from outdated or compromised dependencies. These dependencies can introduce significant security risk if not managed properly. Risk mitigation associated with dependencies can include automated dependency scanning. Regularly scan your project's dependencies using automated tools to identify known vulnerabilities. You can also implement regular updates and dependency pinning. This keeps your dependencies up to date to ensure you're using their latest, most secure versions. And before adding any new dependencies to your project, carefully review its security track record, its maintainers, and its community support. By implementing these strategies, you can proactively manage the risk associated with third-party dependencies, protecting your software from potential security breaches and ensuring its reliability and integrity. Now let's take a look at pipeline configuration and script security. Malicious actors can target the scripts that automate your software build and deployment processes. If these scripts have vulnerabilities or are poorly written, attackers can potentially exploit them to gain unauthorized access, modify your code, or insert malicious components into your software. Misconfiguration within your CI/CD pipeline, such as incorrect permissions, weak authentication, or unpatched software, can create opportunities for attackers. Both these issues underscore the importance of robust security practices throughout a CI/CD pipeline. Let's explore risk mitigation for pipeline configuration and script security. First, you could apply the principle of least privilege. In a nutshell, this means only giving your CI/CD tools the absolute minimum permissions they need to perform their functions. Next, you can implement regular review of pipeline configuration. Your CI/CD pipeline configuration should not be a set it and forget it situation. And lastly, you could use statistical analysis tools for script security. Static analysis tools are like grammar and spell checker for your code, but they specifically look for security vulnerabilities in your scripts. Now let's turn our attention to artifact management. This risk refers to the potential for unauthorized modification or corruption of your software artifacts. If attackers can tamper with your artifacts, they could introduce vulnerabilities, backdoors, or other malicious code. You should implement secure storage and distribution practices. This highlights the importance of protecting your artifacts throughout their lifecycle, from creation to deployment. Risk mitigations associated with artifact management include the use of artifact repositories, signing and verifying artifacts before deployment, and verifying integrity with checksums or hashes. Let's take a look at environment and infrastructure security. In software development, you typically have multiple environments: development, testing, staging, and production. Each of these environments serve a different purpose and may have varying levels of sensitivity. Therefore, risk from misconfiguration environments is a distinct possibility. Even with the best intentions, environments can be misconfigured. For example, ports might be left open, software might not be updated on time, or weak passwords may be set. Now let's take a look at some points for risk mitigation for environment infrastructure security. You can segment and isolate environments. Imagine your infrastructure as a house. Have multiple rooms. Just as you wouldn't want a kitchen fire to spread to the bedroom, you should separate different environments, i.e., separate development from testing and testing from production. This is done to contain any potential breaches. You can also use IAC with security best practices, as well as perform regular audits and monitoring. Another area of concern in security as it relates to CI/CD pipelines is supply chain security. Modern software development often involves a complex web of interconnected components, including third-party libraries, open source code, and various development tools. This complexity makes it difficult to track the origin and integrity of each component, thus creating potential vulnerabilities that malicious actors can exploit. If any element within your software supply chain is compromised, whether it's a library, a build tool, or even the infrastructure where your code is hosted, the security of your entire software system can be jeopardized. Supply chain security mitigations include verifying the source and integrity of components, use supply chain security tools, and perform regular security assessments and audits. Lastly, let's take a look at monitoring and incident response. This involves actively monitoring your systems for any signs of unauthorized access, suspicious activity, or potential security breaches. It also means having a well-defined plan in place to quickly respond to and mitigate any incidences that may occur. To effectively detect and respond to security incidences, you need to have complete visibility into your system. This means implementing comprehensive monitoring tools that can track the behavior of your applications, infrastructure, and network. Monitoring and incident mitigation strategies include implementing comprehensive logging and monitoring, setting up alerts for suspicious activities, and developing and practicing an incident response plan. This entails creating a well-defined plan outlining the steps to be taken in the event of a security incident.
In this topic, we will use Google Cloud Deploy for deployment scenarios. And basically, what we are going to be doing is we are going to use a GitHub repository that is publicly available on GitHub, and it is called Cloud Deploy Tutorials. So you can use this tutorial. Now, the reason that I'm using this particular GitHub repository is because there are a lot of configuration files, there is sample application, everything is readily available. So what we are going to be doing is we are going to take that into consideration and we'll use it as an advantage so that we don't have to set up everything from scratch. Now, there are some commands that we can use. So for example, I need to set up gcloud config set project to SKS001. Now, this is the project that we've been using throughout the course. And then I have already done this part, which is git clone and the GitHub repository. And then we are going to navigate into this directory, which we will do. And then there is this particular file, which is there in this directory called e2e run. Now, before we proceed further, so what I'm going to do is I'm going to take you to that particular place so that you can see. So to be able to do that, I need to activate the Cloud Shell, and I'm going to click on this option called Activate Cloud Shell. And this should open the Cloud Shell. It might even ask us to authorize, which it should do, and we'll just wait for it to open. All right, so it hasn't asked, so that means it was already authorized. Now, what I'm going to do is, now this project is already set up here, so which is gcloud config set project. So it has already set it up. Now, I have already done the cloning part of it. So now if I go ahead and do ls, I should have that particular repository, which is cloud deploy tutorials. Now I need to navigate into this particular directory and then further navigate into the subdirectory. So let's go ahead and copy that command from here. And I am going to use this particular command, copy it, and then I'm going to switch over to the Cloud Shell, right click, paste this command, and then I'm going to press enter. Now, what it is going to do is it is going to now connect us to the Cloud Shell editor. All right. So, which it was already doing. So, now we are already into this particular editor, and notice all these files are there. So, okay, it is initializing the Cloud Shell editor once again. Okay, so it's taken me into that particular directory because in the terminal window, I had given this command. So what it has done is it has opened the editor and taken me into this particular directory. Now, there are certain files that are there. So there is setup.sh, cleanup.sh. So you can simply run this command. If I just go back to my notepad, you can run this command dot setup.sh and it will set up the entire environment for you. You don't have to do anything. And that is the beauty of this particular repository, that it is given you everything. And everything is also specified in the script, what it does. So if I just go back to the editor and if I select this file, it does everything. It sets up the tutorial, root directory, and then application configuration directory, CD configuration directory, and Terraform directory, and gcloud config, which is cloud deploy. And it's a pretty big file. What it does is it basically goes ahead and does a lot of things for you. So, for example, whatever APIs are required to be enabled, it will go ahead and enable that. It will also configure the gcloud settings in Cloud Shell, and it will also create an artifact registry repository, which is going to be required for this particular demonstration. And then it will also create the required service accounts. So whatever service accounts are required, it will create those for you. Now, if I try to run this file, because I've already set up the environment, it will do some parts of it, but then it will also throw errors. For example, when if I just go ahead and run this command dot setup dot sh, if I run this command, it will start. It will take a few minutes to set up the environment. But what happens is, if those service accounts are already existing, it will just throw an error on those service accounts saying that it is already existing. So it's not going to recreate them. So let's just wait for this particular setup.sh script to run. So it's basically doing all the tasks that have been defined. So it's doing exactly one by one, and it is continuing to set up that entire environment for you. And this will continue. This will continue till all these have been completed. So, for example, look at these errors. Error creating service account, Google API, error creating error 409, which says service accounts, this particular service account already exists. So these service accounts are already existing. So therefore, it's not going to recreate these. Rest, everything that was needed to be done, it has already done that. Now, if I just go ahead and let's move back to the editor. So in the editor, if I go to app config, this is where my sample application that is already there. So this sample application is what we are going to be using to create our delivery pipeline. Now there is something called Scaffold. Now Scaffold is an open source continuous development tool set, and that is what is going to be used with Cloud Deploy in this particular scenario. Now there is a scaffold.yml file that exists. So if I just click on this, it shows me the instructions for Scaffold to build container image for your application. Now, this configuration uses Cloud Build Service to build that particular container image for you. So that is there. So now if we just go back to the terminal, the next command that I'm going to execute is, which is going to basically deploy the hello app, hello-app, and that is what it is going to create. So what it is going to do is it will create a container image if I run this particular command. So I'm going to go ahead and paste this command and then press enter. All right. So it is now creating that particular container image. And once this is done, then we can actually go ahead and verify whether this particular container image has been created. So let's move to the notepad and see what is the next command. Now, even though we can verify whether the container image was created or not, but we can simply skip that step and we will just copy this command, which is to create the delivery pipeline. Now this is still creating that particular image. Now it's done. Now, since there are no error messages, I am pretty sure that it has created the container image. So the next one is to create the delivery pipeline. So I'm going to just paste this command which says gcloud deploy apply dash dash file is equal to cloud deploy dash config slash delivery dash pipeline dot yml file. If we just head back to the editor, then we need to go to this particular directory, and we should have that particular file which was called, I need to go back to delivery-pipeline.yml. So there it is. All right. So what it says is hello app, that is the name of the metadata, and then it says deployment pipeline for hello app. And then there are different stages that are going to be there. So I'm going to head back to the terminal and going to press enter to execute this command. All right, so the process of this is already completed. Now the next command that we need to execute is again heading back to the notepad, copying this command to verify the delivery pipeline, whether it was created or not. So I'm going to right click here and paste the command and then press enter. All right, so this was successfully created, but interesting part is, why did we get these three errors? Get target test dash cloud run, staging dash cloud run, and prod dash cloud run. Now, there is a word which is called target because we have not created these targets. Therefore, it was not able to get the environment information on these particular targets. Therefore, you can comfortably ignore these three errors. Now, the next thing that we need to do is we need to create the target, even though there are supposed to be three different targets. And if we just go back here, one is the test dash cloud run, which is we are going to create, and we are not going to create these because the command would remain the same. You have to just change the name of the target. So what I'm going to do is, all right, so it is copied the wrong command. So let me just go ahead and copy this command, come back here, paste it, and let's see what it does. I'm going to press enter. All right, so now it is creating the environment and it's already done that. Once that is done, we can verify the environment and we can simply copy this particular command, and then we can head over to the terminal or the cloud shell and paste this command. And then we should get the information about this particular environment, which is test dash cloud run. So there is the environment information that is there. Now, if I just head back to this notepad and I'm going to go ahead and create a release here. And notice this, initially we had used SKS project one. So everything is happening within your project. Even the release and the test environment, everything is getting created within your project itself. So be sure to change your project name if you are working in a different environment. So you might have a different project name. So I'm going to just go ahead and paste this command to create the release and press enter. And this should now create the release. All right. So it gives a warning which you can safely ignore for the time being. And the next thing is, so, okay, my error. So this is again the same command as the upper one. So we can just go ahead and delete this command. So now this has completed not only the creation of pipeline, but also the release. And similar way, you can create different environments and you can push the release to different environments. So now just to quickly recap in this particular topic, what we did was we talked about the GitHub repository, which is basically used in this particular scenario, from where I had already replicated that repository onto my project. And then basically from there onwards, we followed the process for setting the test environment. We also created a pipeline, and then we also created a release.
Many organizations utilize multiple cloud providers or a combination of cloud and on-premise infrastructure. This slide presents 5 distinct CI/CD pipeline strategies to effectively manage software delivery in these multi-cloud and hybrid environments. We'll explore each of these approaches in the following slides, highlighting their unique characteristics and advantages. The first strategy we will take a look at for multi-cloud and hybrid environments is centralized CI/CD pipeline. This strategy involves creating a unified CI/CD pipeline that manages the entire software delivery process across multiple cloud platforms and on-premise infrastructure. The pipeline orchestrates the build, test, and deployment stages for all target environments. It is most suitable for organizations that have the requirement of unified control and look for simpler management. The next strategy we will investigate is distributed CI/CD pipeline. This approach entails creating a dedicated CI/CD pipeline for each target environment. Each pipeline is tailored for the specific cloud provider or on-premise infrastructure, leveraging its unique tools and services. It is suitable for organizations needing highly customized pipelines for different environments. Next, we will take a look at hybrid CI/CD pipeline. This strategy combines a centralized CI/CD pipeline for common tasks with separate pipelines or deployment tools for each target environment. It aims to strike a balance between centralized control and flexibility. It's ideal for balancing centralized management with environment-specific optimizations. Now let's discuss GitOps-based CI/CD pipeline. GitOps leverages Git as a single source of truth for infrastructure and application configurations. It uses tools like Argo CD or Flux to automate the synchronization of the desired state defined in Git. It's suitable for teams that prioritize declarative configurations and version control. And last, there's Service Mesh Integrated CI/CD pipeline. This strategy involves integrating a service mesh, such as Istio or Linker, directly into a CI/CD pipeline. A service mesh is a dedicated infrastructure layer that manages communication between services in a microservice architecture. It's perfect for microservice architectures requiring advanced traffic management and observability across environments. Now let's turn our attention to key components of binary authorization. Binary authorization is a security control mechanism that verifies the identity and integrity of software binaries before they are executed. The first component we take a look at is signature verification. Binaries are digitally signed using cryptographic keys. During the authorization process, the signature of the binaries is verified against a trusted public key to ensure its authenticity. Next, we take a look at policy enforcement. Binary authorization policies define the criteria for accepting or rejecting binaries based on factors such as their source, integrity, and compliance with security standards. Last, immutable artifacts. Once a binary is signed and authorized, its contents remain immutable. The importance of binary authorization in securing software supply chains starts with preventing supply chain attacks. Binary authorization acts as a barrier against supply chain attacks where malicious actors attempt to inject unauthorized or compromised code into software repositories or deployment pipelines. That's followed by ensuring trustworthiness. By enforcing strict unauthorized policies, binary authorization ensures that only trusted sources and verified code are allowed into production environments. Then you would implement compliance and regulatory requirements. Many industries and organizations are subject to regulatory requirements and compliance standards. They mandate the use of secure software development practices. And finally, mitigating insider threats. Binary authorization controls can also help mitigate insider threats by restricting the deployment of unauthorized or malicious code by internal actors. Benefits of binary authorization are stronger security. It helps prevent unauthorized or malicious software from entering your environment and reduces the risk of attacks and data breaches. Improved compliance. It can help you meet the regulatory requirements for software security and auditability. Increased confidence. You can deploy software with greater confidence after it has passed rigorous security checks. And lastly, automated enforcement. This is the process of verifying software integrity, reducing the need for manual checks. For example, you can secure a GKE cluster by using binary authorization. First, you would start by enabling binary authorization. This makes binary authorization available for your GKE cluster so that you can set up policies and enforce attestation. Next, you would create attesters. Attesters are entities that can verify and sign container images, confirming that they meet your security standards. Next, you can define appropriate policies. Policies are rules that govern what kind of attestations are required for a container image to be deployed. And last, you would deploy and verify. When you deploy a container image to your GKE cluster, binary authorization automatically kicks in. In software development, secrets are like the combination to a safe. They include API keys, passwords, certificates, and other sensitive data. Just like the combination to a safe, if these secrets are exposed, anyone can gain unauthorized access to your valuable assets, causing potential harm and disruption. The importance of secret management is to protect sensitive data, maintain system integrity, comply with regulations, and ensure business continuity. Consequences of mishandling secrets could include data breaches, system compromise, financial losses, and reputation damage. To implement secret management in CI/CD pipelines, you would first need to choose a secret management tool. Then store your secrets securely. Next, you would integrate with CI/CD tools, and then implement access control. And last, set up rotation and auditing. Best practices for secret management would include to not hardcore secrets, use a secret management tool, limit access to secrets, rotate secrets regularly, encrypt secrets in transit and at rest, and finally, audit and monitor access.
In this topic, what we are going to do is we are going to run a vulnerability scan while we are generating a build. Now, to be able to do that, we are going to use on-demand scanning from Google Cloud Platform. And before we do the scanning part, what we are going to do is open the editor, and I'm going to walk you through a few files that I have created for this build. And of course, this is cloudbuild.yml file that is there. We are going to have a walkthrough of that. And then there are a few more files that we will talk about. So once this particular editor opens, I am going to go to my projects, which is ODS tutorial, and there is this cloudbuild.yml file. Now this file basically it builds a Docker image, it scans for vulnerabilities and then handles the results, and then it does a lot of other things like get the digest of the build image for scanning, start the on-demand scan, wait for scan to complete, analyze vulnerabilities, push the Docker image only if no critical or high vulnerabilities unless the image built by this configuration. There is the Docker file that is there. It is a very simple file which basically runs two commands. I open the terminal and clear the screen. I'm going to run this particular command. What it is going to do is if there are no vulnerabilities which are supposed to be critical or high vulnerabilities, it is going to generate the build. And if there are any vulnerabilities that are there, then it is not going to do that. I'm just going to go ahead and press enter. But before that, it is gcloud builds summit config cloudbuild.yml file. And that YML file, which is the cloudbuild.yml file, we have just gone through. So I'm going to go ahead and press enter. Now this takes a little time because Cloud Build creates a temporary archive of couple of thousand files, and it takes a bit of time in doing that. So once this is done, it will start the build process. And this is going to fail at step 0 itself because there are vulnerabilities that are there. It is not going to generate the build. It is going to simply generate a failure message, and that is what the intent is. Because you want to find out if there are vulnerabilities, it should throw an error and stop the build generation. And beyond that, we can go into logs, we can review the logs and figure out what the vulnerabilities are. And you can do a lot of other things, but we are going to halt at this point where the build fails. And the intent is to show you, if you integrate this kind of vulnerability on demand scanning, then you will not end up with a build which has vulnerabilities. So we are going to just let this process run. It is going to be a little more time consuming, but that is going to be okay. Now let's move to the next step, which is uploading tarball of .2gs. It is uploading to a cloud storage bucket, and now the build process starts, and very soon we are going to encounter an error, and after which build will fail and we will get a failure message. All right, so it has not gone beyond that. Somewhere it has encountered a particular error, and that's where it has exited. And now we are faced with a failure message. Now, just to quickly recap, in this particular topic, we talked about a particular method which is on demand vulnerability scanning to be performed while build is getting generated. Now, if there are no vulnerabilities which are severity high or critical, then the build passes, and if it encounters any of those errors, then the build generation fails. And that is exactly what we saw, that the build generation failed. In this topic, what we are going to do is discuss about IAM policies for different build environments. There are different build environments which could be testing, staging, production. Now, what we need to do is we need to basically build 4 different service accounts and use them with 4 distinct triggers that we are going to use. For example, I have this trigger called Cloud Build Dev, Cloud Build Prod, Cloud Build Staging, and Cloud Build Test. Now, if I click on Cloud Build Dev, and I will scroll down once it loads up, and I will just go ahead, and I have a service account which is SKS-Dove and the service account name. So this is the service account. Now, each of these service accounts that I'm going to be using, I will have distinct permissions or roles assigned to them. Now, before we do that, let's see, we are connected to the same repository in the GitHub bucket. This is SKS product and the branch is main. All these triggers are linked to the same GitHub repository because we'll be using the same set of code to create the build. And then notice that there is a distinct change in the usual way. We used to write cloud build.yml file, either store it in the repository on GitHub, or we used to have it inline. This time, there is a subdirectory in the GitHub repository that is there, and this subdirectory is called .cloud build. Now, if I hop over to GitHub, notice that in my repository SKS product, there is a subdirectory called .cloud build. With this .cloud build subdirectory, I'm going to go ahead and click on it, and we will find 4 YML files. There is cloud build -dev, -prod, -staging, and -test. Now, if I go ahead and click on cloud build -product YML file, I'm going to see the code that is there. Now, that code depends on what you are trying to build in the pipeline. You can have that particular code here. Now, this is just the sample code that I have defined here. Now, if I go back to .cloud build subdirectory, I will have 4 different files with 4 distinct codes that are meant to build separate pipelines for each of these stages, which is dev, prod, staging, and testing. Now, if I come back to the trigger, this trigger, what it was, dev. If I go back and I go ahead and open the prod trigger, which is cloud build -prod, now this will have a particular YML file linked. This is .cloud build / cloud build -prod.yml file that is there. So notice that there is the subdirectory that is prefixed in the path. Now, since we have not made any specific changes, we are going to go ahead and cancel it. And before that, the service account is SKS-prod @ with usual suffix with your project name and the email domain name. I'm going to go ahead and cancel it. Now we are going to talk about this particular service account that is linked to it. I'm going to go to IAM and go back and get the list of all service accounts I have. I'm going to target this SKS-prod. Now, as and when I make changes to this service account and the policy linked to it, it will automatically get updated. Now, we want to check what permission it has. I'm going to go ahead and click on permissions, and then I'm going to go ahead and click on view access. Notice that there is policy analyzer that opens up. We will see the set of privileges. Now, what I need to do is I am going to click on analyze and then click run query. It will give me all the roles that are assigned to this particular service account. Look at the number of roles assigned. This is compute admin, Kubernetes engine admin, storage object viewer, cloud build editor. All these roles are assigned because they are meant for a specific task. Each role is meant for something. So, for example, there are certain container related tasks that this role must be doing, and that is the reason there is Kubernetes engine admin. Then it might also need to browse a bucket. So therefore, the storage object viewer is there. And then because you need to run builds and generate them, the cloud build editor permission is also assigned to each of these roles. For example, if I just go back to the service accounts, and if I go ahead and look at SKS-dev, if I click on this, I go to permissions and click view access. Just like the prod service account, this is going to open policy analyzer, and then we are going to run the query to view its role that have been assigned. I'm going to go ahead and click on analyze and click on run query. So it lists the roles. This one has 3 roles assigned: storage object viewer, and cloud build editor. The intent is that for different environments that are linked to a single GitHub repository, you can have different set of IAM policies that are linked to individual accounts. Every single service account will have policy linked, and this policy defines what kind of roles are assigned to this particular service account. And depending on what your service account is performing, it is going to have all those roles assigned. And now, once you take the service account and link it to a particular trigger, and depending on what your cloud build.yml file is doing, you might need to tweak the roles that are assigned to this particular service account. For example, you might need to add another role because it throws an error that you don't have sufficient permission to generate a cloud build, for example. You might need to assign cloud build editor role to that particular service account. Now, just to quickly recap, in this particular topic, we talked about the different environments that have different service accounts, but all these are linked to a single GitHub repository, and every single service account has a certain set of privileges and roles assigned, and those can be viewed by Policy Analyzer. And this is exactly what we did in this particular demonstration.
Now let's take a look at a case study. Acme Software is a fast-growing technology company that develops a popular web application. They've adopted a CI/CD approach to rapidly deliver new features and updates to their customer. They face the following challenges: code vulnerabilities, insecure secrets, compromised CI/CD systems, and unpatched dependencies. To address their challenges, Acme Software implemented a multi-layer security strategy. They implemented code scanning, secret management, access control, network security, dependency scanning, image scanning, immutable infrastructure, and monitoring and logging.
In this topic, you will learn how to deploy a simple Node.js function to Google Cloud Functions using Cloud Build and Cloud Shell. Cloud Functions is a serverless computing service that allows you to run your code in response to events without the need to manage servers. By the end of this demonstration, you will have a basic understanding of how to create, configure, and deploy Node.js function in a serverless environment using Google Cloud Platform tools. Now, there are certain prerequisites that you need to meet. So you need to have a Google Cloud Platform account, which is obvious. And then you also need to have the Cloud Functions and Cloud Build APIs enabled. And you would also need access to the Cloud Shell. So what we are going to do is we are going to open the Cloud Shell, and I have already done that. So I am right now in the editor mode. So here I have this particular directory which is called simple dash function, and in this particular directory I have these three files, which is cloudbuild.yml, index.js, and package.json. Now let's look at the index.js file first. So this is a very simple file. What it does is it exports a single function named hello world. Now, this function is designed to handle HTTP requests and send a simple response back to the client. Now, let's talk about the code a little bit. So there is export.hello world, which is the entry point for the function. It means that when this function is triggered by an HTTP request, the code inside it will be executed. Then we have rec res, which are the requests and response objects provided by HTTP request. Then there is rest.send, and then there is a message which is hello from Cloud Functions, which sends a response back to the client with the message hello from Cloud Functions. Now, this file is the heart of your Cloud Function, and this is where your actual business logic resides. This file is pretty simple, but obviously in your real life environment, you might have lot of configuration stored within this particular file. Let's now talk about package.json file. Now, this is a configuration file that is used in Node.js projects. It contains metadata about your project, including its dependencies, scripts, and other settings. So let's quickly look at what this file is. So there is a key value pair, which is name and simple function. That is the name of your project. Then there is version, which is 1.0.0. That is the version of your project. And then there is description. You can add whatever description you want. And then the next one is the main, which has the value of index.js. Now it specifies the entry point for your application. Here it is going to be index.js, which means it is pointing to index.js file. Then there is scripts. So in bracket, it has start colon node index.js, which defines a command that can be run using npm start. It tells Node.js to start the application using index.js file. Then there is dependencies in which you can list any Node.js package your project depends on. In our case, there is no external dependencies, therefore it is blank. Now, this file is critical for defining how your project should be managed and executed. Then there is the cloudbuild.yml file that I have already defined. And let me just authorize this. So somehow this has popped up all of a sudden. So we authorized it to go ahead. Now, cloudbuild.yml file is a configuration file for Google Cloud Build. It defines the steps that Cloud Build will follow to deploy your cloud functions. The purpose of this file is to automate the deployment of your cloud function using Google Cloud Build. Now, there are again, just like both the files, there are key sections in this file. So there is steps which lists the steps that Cloud Build will execute. So there is name, which specifies the name. Then there is name, which specifies the Cloud Build builder image to use, which in this case is Google Cloud SDK. Then there is args, which provides the argument to the gcloud command. So there is function deploy hello world, which deploys a cloud function named hello world. Then there is runtime node.js 14, which specifies the runtime environment as node.js version 14. Then there is trigger HTTP, which configures the function to be triggered by an HTTP request. Then there is an entry point hello world, which specifies the entry point for the function, which matches the name of the function exported in index.js file. Then there is memory, which allocates around 256 megabyte of memory for this function. And then finally, we have the last section, which is options that configures additional build options. Now we have logging here, which is set to cloud logging only. This specifies that the build log should be stored only in cloud logging. Now, with all this, we are ready, and the next thing we need to do is what we are going to do is click on open terminal, and the terminal will open, and we are going to basically navigate into that directory, which is cd simple. If I just go ahead and do this, it will give me the complete name, and here we are going to enter this command called gcloud builds submit dash dash config. Then you have cloud build .yml, and I press enter. Now this should generate a build for us. Now basically, this is the way you need to build an application if you want to use serverless function along with cloud build. Even though this one was pretty simple, but if you just follow the same approach, you should be able to deploy even a larger application. And of course, the configuration settings will differ. There is no doubt in that. But the thing is, the process still remains the same. You need those files, index.js, you need package.json, and you would also need cloudbuild.yml file, and they all must be stored within that single directory that I had created earlier, which is simple-function. So we are just waiting for the build to complete, and it should get completed pretty soon. Now, once the deployment is complete, you can actually go ahead and test the function by making an HTTP GET request to the deployed endpoint. Now the deployment is complete, you can actually go ahead and test the function by making an HTTP GET request to the deployed endpoint. Now in this particular demonstration, we successfully deployed a node.js function to Google Cloud Functions using Cloud Build. We've reviewed 3 different files, which were index.js, package.json, and cloudbuild.yml file. And then we executed the command, which is gcloud build submit, and we gave cloudbuild.yml file as the parameter, and that is how we were able to successfully create this build.
By auditing and tracking deployments in GCP, you gain visibility, control, and insight into your environment. This helps you maintain accountability, troubleshoot issues faster, strengthen security, comply with regulations, and continuously improve your development and deployment processes. Here are some best practices for auditing and tracking GCP deployments. Enable audit logging. Use cloud logging. Leverage cloud audit logs. Tag your resources. And implement version control for deployment configurations. Utilize Deployment Manager or Terraform. Integrate with third-party tools. Establish clear policies and procedures. And perform continuous monitoring and review. Here's some examples of tracking deployments with cloud logging. Make sure it's enabled for Cloud Deploy and other relevant services. In Cloud Logging, use the Log Explorer to filter for audit logs related to Cloud Deploy. You can filter by resource type, user, or actions. Set up alerts to be notified when specific deployments occur or when they're either failures or rollbacks. In summary, we took a look at advanced techniques for managing CI/CD pipelines and integrating third-party CI/CD tools, security challenges and mitigations with CI/CD tooling, and using Google Cloud Deployment for complex deployment scenarios, CI/CD pipeline strategies for multi-cloud and hybrid environments, and the role of binary authorization in securing software supply chains. We also took a look at implementing secret management practices in CI/CD pipelines and applying vulnerability analysis tools in the CI/CD process, IAM policy configurations for CI/CD pipelines, and exploring a case study for securing a CI/CD pipeline. And lastly, CI/CD pipelines for serverless applications on GCP and best practices for auditing and tracking deployments in GCP. Coming up next, we'll take a look at Foundations of Site Reliability Engineering, or SRE. Welcome to Foundations of Site Reliability Engineering. I'm Ron Johnson. In this course, we will take a look at defining the principles and key components of site reliability engineering, describe the concepts of error budgets and their role in balancing reliability and development speed, establish service level objectives related to service level agreements, describe the strategies for automating toil and repetitive tasks to improve operational efficiency, outline the importance of opportunity cost in risk and reliability decisions, describe the implementation of capacity planning and its impact on service reliability. Use Google Cloud tools for auto-scaling resources effectively. Identify service level indicators. Analyze the role of feedback loops in enhancing service performance and reliability. Compare different models for managing the service lifecycle from introduction to retirement. Describe the importance and elements of a culture of learning and blamelessness in an organization. And finally, outline case studies where implementing SRE practices lead to improved service reliability and efficiency. Site reliability engineering is a discipline that combines software engineering and system engineering to ensure that large-scale services are reliable, efficient, and scalable. SRE teams use their technical skills to manage and automate the operation of complex systems, focusing on reliability as a key feature. Now let's take a look at some core principles. Reliability is treated as an essential feature of the service equally important as any other functionality. SRE ensures services are reliable and available to users. SRE teams set specific measurable targets for reliability known as SLOs. These objectives define acceptable levels of uptime and performance. An error budget quantifies the allowable amount of downtime or service failure. It helps balance the need for innovation and reliability by defining acceptable risk levels. SRE emphasizes automating repetitive tasks and creating tools to manage systems more efficiently. Automation reduces manual work and minimizes human error. Engineers respond quickly to incidences, using predefined processes to mitigate the impact of the incidents and resolve issues efficiently. Incident management ensures quick recovery from disruptions. After an incident, SRE teams conduct postmortems to analyze what happened, understand the root causes, and learn how to prevent similar issues. The focus is on learning, not blaming. Robust monitoring systems detect issues early. It helps understand the internal state of a system by analyzing the data it generates, like logs and metrics. And finally, SRE ensures that systems can handle current and future loads by forecasting demand and planning for capacity. This avoids outages due to overload. Now let's take a look at key components of SRE. Incident management uses tools and processes to respond to, manage, and resolve service disruptions quickly. This includes alerting systems, on-call rotations, and incident playbooks. Monitoring and alerting checks the health of services and alerts the teams when issues arise. This includes metrics, logs, and tracing systems. Scripts and software that automate repetitive tasks like deployment, scaling, and recovery. Automation reduces minimal intervention and speeds up processes. Service level indicators are metrics that measure specific aspects of a service performance, such as latency, error rates, and throughput. SLIs help evaluate whether SLOs are being met. And last, configuration management. Systems that manage and control the configuration of infrastructure and applications, ensuring consistency and preventing issues caused by configuration errors. Other key components of the SRE environment include change management. These are processes to manage and document changes to the system, including version control, code review, and deployment strategies, like canary releases and blue-green deployments. Capacity management. These are tools and techniques to monitor resource usage and predict future needs, ensuring efficient scaling without over-provisioning. Resilience testing. These are techniques like chaos engineering, where systems are intentionally stressed to find and fix weaknesses, ensuring services can withstand unexpected conditions. Collaboration and communication tools. These are platforms that facilitate collaboration among team members, especially during incident response. This includes chat systems, documentation tools, and project management software. And last, security and compliance. Practices to ensure that systems are secure and comply with relevant regulations. This includes regular security audits, vulnerability scanning, and adherence to compliance standards. Imagine you have a monthly spending budget with limits for entertainment, groceries, and other expenses. An error budget is similar, but instead of money, it's about how much your computer system is allowed to misbehave. This misbehavior can include downtime. The system is completely unavailable. Slowness. The system takes too long to respond to users. Errors. Users encounter error messages or malfunction features. The error budget is the total amount of this misbehavior that is considered acceptable over a certain time period, like a month. The primary purpose of the error budget is to create a measurable and agreed upon tolerance for failures. This allows teams to understand how much risk they can take while still meeting reliability targets. Error budgets are based on something called an SLO, Service Level Objective. An SLO is a goal for how well you want your systems to perform. For example, a common SLO is 99.9% uptime, meaning the system should be available 99.9% of the time. To calculate the error budget, you subtract the SLO from 100%. So in our example, 100% minus 99.9% equals 0.1%. This means the system is allowed to be unavailable 0.1% of the time and still meet its performance goals. Error budgets help balance the need for maintaining high reliability with the desire to release new features and updates quickly. By quantifying the acceptable amount of downtime, teams can make informed decisions about when to prioritize stability and when to focus on innovation. Error budgets provide development teams with a degree of freedom to experiment and innovate. When the error budget is available, teams can confidently release new features and updates, knowing they have a cushion to accommodate potential issues or unexpected downtime. This fosters a culture of innovation and risk-taking, encouraging teams to push boundaries and deliver new functionality faster. When the error budget is depleted or nearing exhaustion, it signals that the system's reliability is at risk. This prompts teams to shift their focus toward addressing underlying issues, fixing bugs, and enhancing the system's stability. The error budget functions as a trigger, prompting teams to prioritize reliability efforts and ensure that the system remains within acceptable performance limits. The budget provides teams with a clear understanding of how much risk is acceptable. It encourages controlled risk-taking by providing a clear threshold for acceptable failure. This means that teams can experiment and push new features as long as they stay within the error budget. Error budgets provide a quantitative measure for addressing the impact of change on a system's reliability. By tracking the consumption of the error budget, teams can make data-driven decisions about when to release new features, when to prioritize stability improvements, and when to investigate potential issues. This approach avoids subjective judgments and ensures that the decisions are based on concrete evidence. SRE teams continuously monitor the system's performance against the error budget. They track incidents and downtime to ensure that the service stays within the allowable limits. This monitoring helps teams respond quickly when they approach the limit defined in the error budget. When the system operates within that budget, development teams can prioritize new features and updates. If the error budget is exhausted, they can focus on addressing reliability issues. This dynamic prioritization helps balance short-term and long-term goals. Now let's turn our attention to establishing SLOs. First and foremost, you would want to identify key services. Figure out the most important part of your system that directly impacts users. This could be website uptime, the response time of an app, or the success rate of data backups. Next, you would want to choose the relevant metrics. Select specific measures of performance for each service. For uptime, the metrics would be the percentage of time the service is available. For response time, it could be the average time taken to load a page. Next, set realistic targets. Don't aim for perfection. SLOs should be challenging but achievable. They should be based on what your users expect and what your systems can realistically deliver. For example, 99.999% uptime might be impossible, but 99.9% might be a good goal. Then align with business goals. Make sure your SLOs support the overall goal of your organization. If your company prioritizes customer satisfaction, your SLOs might focus on responsiveness and error rates. And last, communicate clearly. Make sure everyone involved understands the SLOs and what they mean. This includes developers, operation teams, and even business stakeholders. Now let's take a look at service level objectives and their integration with service level agreements. SLOs and SLAs are two interconnected concepts that are essential for defining, measuring, and ensuring the quality of a service. SLO serves as an internal target for a service provider. They define the desired level of performance for a specific aspect of a service, such as availability, latency, throughput, or error rate. As stated earlier, an SLO might specify that a website should be available 99.9% of the time, or that an API should respond to a request within 200 milliseconds. SLOs are not vague promises, but measurable goals with specific metrics to enable objective evaluations of services, performance, and to identify areas of improvement. SLAs are formal agreements between a service provider and a customer. They outline the expectations for service quality, including specific SLOs that the provider commits to meeting. SLOs included in an SLA provide clarity to both parties. They establish a common understanding and help manage customer expectations. SLAs often include clauses that specify consequences for the service provider if they fail to meet the agreed upon SLO. These consequences can include financial penalties, service credits, or other remedies. The potential consequences outlined in SLAs create a strong incentive for service providers to maintain high-level service and meet their SLO targets. SLAs prompt service providers to focus on reliability and ensure customers receive the quality of service they expect. Let's now take a look at an example of service level objectives integrating with service level agreements. Imagine a company that provides cloud storage services. Their SLA with a customer might include the following SLOs: 99.95% uptime, 11.9 durability, meaning minimal data loss, average of 100 milliseconds for data retrieval. The SLA would specify the consequences if these SLOs are not met, such as a service credit for each hour of downtime beyond the agreed upon threshold. These SLOs and SLA ensure that the customers receive reliable and high-performance storage service, and that the service provider is accountable for meeting their commitments. Now let's turn our attention to strategies for automating toil and repetitive tasks. Automating toil and repetitive tasks is essential for improving operational efficiency and allowing teams to focus on more valuable and strategic work. It's not just about implementing tools, but also about fostering a cultural shift that embraces automation as a way to improve productivity and job satisfaction. Here are some strategies for achieving this goal. The first step is to identify tasks that are repetitive, manual, and time-consuming. These tasks often include routine maintenance, monitoring, data entry, and deployment processes. Once toil tasks are identified, assess their potential for automation and prioritize them based on their impact on operational efficiency. Consider the complexity, frequency, and value of each task to determine which one should be automated first. Focus on tasks that offer the most significant time saving, error reduction, or improved reliability. Leverage automation tools and frameworks to implement solutions, always keeping security in mind. For example, use configuration management tools like Ansible, Chef, or Puppet to automate infrastructure setup and maintenance. Use infrastructure as code tools like Terraform or AWS CloudFormation to automate the provisioning and management of cloud resources. Ensure that your IAC configuration follows security best practices to protect your infrastructure. CI/CD pipelines automate the process of building, testing, and deploying code. Tools like Jenkins, GitLab CI/CD, and Circle CI help streamline these workflows, reduce manual intervention, and integrate security checks at every stage. Set up automated monitoring and alerting systems to keep track of your system's performance and health. Tools like Prometheus, Grafana, and Nagios can automatically detect issues and notify the team without manual checks, enabling rapid response to potential security threats or performance problems. More strategies for automating toil and repetitive tasks would include writing secure script to handle routine tasks such as backups, log rotation, and software updates. Scripting languages like Python, Bash, and PowerShell can help you automate these processes effectively while incorporating security measures like input validation and error handling. Use job schedulers like cron for Unix and Linux or Task Scheduler for Windows to run automated tasks at specific intervals. This ensures tasks are performed regularly without manual initiation, while also providing an opportunity to schedule security scans and audits. Develop self-healing mechanisms that automatically detect and resolve common issues. For example, configure systems to automatically restart failed services or scale resources based on demand. Ensure these mechanisms are designed with security in mind to prevent unauthorized actions. Integrate automation with chat platforms like Slack or Microsoft Teams using ChatOps. This allows team members to trigger automated tasks securely and view results directly within the chat interface, facilitating collaboration and incident response. Document the automation process thoroughly, including security considerations, and create standardized templates and scripts. This ensures consistency, maintainability, and knowledge sharing within the team. Continuously review and improve automated processes based on feedback and performance metrics. Identify new areas for automation, refine existing solutions to enhance efficiency, and incorporate feedback from security audits to strengthen your automation practices. To obtain your goal of automating toil and repetitive tasks, consider these processes. Train and provide resource to team members on using automation tools, writing secure scripts, and understanding security best practices. Empowering the team fosters a culture of automation and security awareness. Track the impact of automation on operational efficiency and security by using key performance indicators. Use these metrics to demonstrate the value of automation, identify further improvement opportunities, and ensure the ongoing security of your systems. And finally, ensure that the automation solutions are integrated across different systems and platforms to create a seamless and secure workflow. This integration helps eliminate silos and ensures end-to-end automation of processes while maintaining security controls across the entire system. Now let's transition to a new subject, opportunity cost. This concept explores what opportunity cost entails, provides an illustrative example, and underscores its significance in risk and reliability assessment. Understanding opportunity cost is crucial in managing risk. Every decision incurs an opportunity cost. Opportunity cost is defined as the value of the best alternative foregone when a decision is made. By carefully evaluating opportunity cost, one can make informed decisions that strike a balance between the risk and reward of various options. It represents the potential benefit or gains lost due to choosing a specific course of action. In the realm of risk and reliability, it involves weighing what is sacrificed by opting for one path instead of another. Consider having limited time and money, facing a choice between two paths. Option A involves dedicating your weekend to resolving bugs and enhancing the reliability of your software. This choice prioritizes stability, reducing the likelihood of crashes or errors. However, it means foregoing the opportunity to introduce an exciting new feature. Option B entails spending your weekend on developing a new feature aimed at attracting more customers. This option prioritizes innovation and potential growth, offering a cool new feature but potentially leading to a less stable software with more bugs. Choosing option A means missing out on potential customer growth and increasing revenue that could have come with developing the new feature. Choosing option B means risking potential downtime, user frustration, and lost revenue due to a less reliable system. The importance of opportunity cost in decisions concerning risk and reliability is paramount in technology. Resource allocation is critical, as resources such as time, money, and personnel are limited. Each decision regarding risk and reliability requires allocating these finite resources. Opportunity cost prompts evaluating trade offs and making informed decisions on where to invest resources for maximum benefit overall. It necessitates considering not just what you gain, but also what you forego. For example, prioritizing resources to enhance the reliability of one system may mean missing opportunities in other areas of the business. In risk management, weighing the opportunity cost of each option is crucial. Intensive investment in certain security measures might lower specific risk, but could divert resources from critical areas like future development or performance optimization. Evaluating opportunity cost helps balance risk versus gains, enabling informed decisions on managing and mitigating risk effectively. Balancing reliability and innovation poses a perpetual challenge in the tech sector. Excessive focus on reliability might hinder innovation and slow progress, whereas an extreme emphasis on innovation can jeopardize system stability. Opportunity cost assists in finding a middle ground by assessing the potential benefits and trade-offs of each approach. And finally, long-term planning benefits from opportunity cost analysis in risk and reliability decisions. Anticipating the future implication of choices helps avoid short-sighted decisions that could lead to future complications. Rather than focusing solely on immediate gains or losses, it encourages consideration of the enduring consequences of decisions over time. Capacity planning is essential for managing IT infrastructure. It ensures your systems have the necessary resources to handle current workloads and anticipated future demand. Here's a detailed breakdown. Capacity planning involves determining the resources needed to meet present and future workload demand in an IT environment. The primary goal is to ensure your system can handle increased workloads without compromising performance or reliability, thus helping to avoid system crashes, slow performance, and other resource-related issues. The first steps in capacity planning would be gathering data. Start by understanding your current service usage. Track data such as number of active users at different times of the day, most popular features, and amounts of data being stored and transferred. Second, forecast demand. Predict future usage changes based on factors like seasonal trends, marketing campaigns, and new features or products. Third, calculate capacity needs. Use your data and forecast to determine the required resources, servers, storage, bandwidth to meet user demand. Include a buffer to handle unexpected spikes. Next, acquire resources. Once you have identified your needs, start acquiring the necessary resources by buying or renting more servers, increase storage capacity, upgrade your network connections. And last, monitor and adjust capacity. Continuously monitor your service's performance and adjust capacity as needed to maintain optimal performance. Proper capacity planning is crucial for maintaining a reliable service. Here's how it impacts various aspects. Preventing slowdown and crashes. Insufficient capacity can cause your service to become slow, unresponsive, or even crash completely when user demand exceeds available resources. An example would be if a website experiences a sudden surge in traffic due to a promotional campaign. Inadequate capacity could lead to slow loading times or make the site inaccessible to users. Increase user experience. Ensure adequate capacity keeps your service fast and responsive, even during peak usage, leading to a smooth and enjoyable user experience. This is crucial for user satisfaction and loyalty. For example, an online learning platform that performs optimally even when thousands of students access it simultaneously during a live class. This will encourage continued use by providing a positive experience. Preventing outages and downtime. Capacity planning helps prevent service disruptions and downtime by anticipating and provisioning necessary resources. You can handle unexpected traffic spikes or increase usage without interrupting service availability. Here, a financial institution that accurately forecasts high transaction volumes during tax season can allocate enough resources to ensure uninterrupted service for its customers. And finally, optimizing cost. Capacity planning balances the cost of adding resources with the need to maintain service reliability. Overspending on resources that aren't fully utilized is wasteful, while skimping on resources risks service outages or poor performance. Effective capacity planning ensures you have enough resources to meet demand without overspending. An example here would be a company can significantly reduce its cloud infrastructure cost by adjusting its resources based on real-time traffic patterns, instead of constantly maintaining maximum capacity. Capacity planning is not a one-time activity. It's an ongoing process that requires constant monitoring and adjustment, regularly assessing system performance, identifying bottlenecks or issues, and making the necessary changes to ensure optimal performance and reliability. The simplest form of autoscaling is to scale a managed instance group. You can autoscale based on load balancing service capabilities, CPU utilization, monitoring metrics, or schedules. We will take a look at all four of these in this demo. Here we see the instance group page. The first thing we would do would create an instance group. Here you would give the group a name. Next, you would select an instance template. I took the liberty of creating one of these earlier. Next, you would select the zones by which you want to deploy. Here we'll turn auto scaling off, thus to show you how to actually invoke it once we create an instance group. The rest you can leave as a default. Now create. Once the instance group has been created, you would then go and edit the group. Now, as you can see, we turned auto scaling off. We will now invoke auto scaling and initially set it for CPU utilization. We will select Scale Out, only add instances to the group. We will have a minimum number of 1 and a maximum number of instances at 10. Next, we would select the CPU limits by which we would want to scale. Simply select the down arrow and change 60 to 75, for example. Leave the rest of the settings as default, and then click Save. The instance group has been successfully updated and now will auto-scale once the CPU utilization reaches 75%. One further note on autoscaler. The autoscaler treats the target CPU utilization level as a fraction of the average use of all virtual CPUs over time in the instance group. If the average utilization of your total virtual CPU exceeds the target utilization, the autoscaler adds more VM instances. If the average utilization of your total virtual CPUs are less than the target utilization, the autoscaler removes instances. For example, setting a 75% target utilization tells the autoscaler to maintain an average utilization of 75% among all vCPUs in the instance group. Next, we'll take a look at predictive autoscaling. Predictive autoscaler forecasts your scaling metrics based on the metric's historical trends. Forecasts are recomputed every few minutes, which lets the autoscaler rapidly adapt its forecast to very recent changes in load. Predictive autoscaler needs at least 3 days of history from which to determine a representative service usage pattern before it can provide predictions. Compute engines use up to 3 weeks of your MIG's load history to feed the machine's learning model. Now we'll take a look at enabling and disabling predictive autoscaling. We'll take a look at our demo group, instance group. We'll edit. Here we find that autoscaling is once again turned off, so we will have to turn this on. Select Add and Remove Instances to the group. Once again, we can specify minimum and maximum number of instances. Next, you will need to select CPU utilization. Under CPU utilization, you will see predictive autoscaling. We will turn this on to optimize for availability. Then select Done. Under initialization period, specify how long it takes for your application to initialize a new instance. This setting informs predictive autoscaler to scale out further in advance of anticipated load, so that the applications are initialized when the load arrives. This is currently set at 60 seconds. Then click Save. You can visualize the historical size of your group using cloud monitoring. The monitoring graph shows how your auto-scale configuration scaled your group over time, and it also shows how predictive auto-scaling, if enabled, would have scaled your group. Here are the steps. Select Overview of the group that has predictive auto-scaling turned on. Then go to Monitoring. Highlight the name of the first chart in the actual Overview section, and then select Predictive Autoscaling. If your service takes a long time to initialize, your users might experience service latency after a scaled-out event. That is, while the new VMs are provisioned but not yet servicing. Predictive autoscaling takes into account your application's initialization time and scales out in advance of predicted increases in usage, helping you to ensure that the number of available service instances are sufficient for the target utilization. Compute Engine provides support for load balancing within your instant groups. You can use autoscaling in conjunction with load balancing by setting up an autoscaler that scales based on the load of your instances. The balancing mode and the target capacity that you specify define the conditions under which Google Cloud determines when a backend VM is at full capacity. Google Cloud attempts to send traffic to healthy VMs that have remaining capacity. If all VMs are already at capacity, the target utilization or rate is exceeded. Compute Engine provides support for load balancing within your instance groups. You can use autoscaling in conjunction with load balancing by setting up an autoscaler that scales based on the load of your instances. The balancing mode and the target capacity that you specify define the conditions under which Google Cloud determines when a backend VM is at full capacity. Google Cloud attempts to send traffic to healthy VMs that have remaining capacity. Now let's take a look at enabling autoscaling based on load balancing server capacity. We'll start at the instance groups. Select an instance group, then select Edit. Once again, turn on autoscaling. Also select your maximum and minimum number of instances. Next, we will add a signal. Then we will select HTTP load balance utilization. Enter the target HTTP load balance utilization. This value is treated as percentage. For example, for 60% HTTP load balancing utilization, enter 60. You can use the cooldown period to set the initialization period, which tells the autoscaler how long it takes for your application to initialize. Specify an accurate initialization period. This improves autoscaler's decisions. For example, when scaling out, the autoscaler ignores data from VMs that are still initializing, because those VMs might not yet represent normal usage of your application. The default initialization period is 60 seconds. Then save your changes. You can set one of three options for your load balancing service capacity. When you first create the backend, you can choose among maximum backend utilization, maximum requests per second per instance, or maximum requests per second of the whole group. For example, if you set a backend to handle 10 requests per second per instance, and the autoscaler is configured to maintain 80% of the rate, then the autoscaler can add or remove instances when the request per second per instant changes. Now let's take a look at scaling based on schedules. Schedule-based autoscaling lets you improve the availability of your workloads by scheduling capacity ahead of anticipated load. If you run your workload on a managed instance group, you can schedule a required number of virtual machine instances for recurring load patterns, as well as one-off events. You can also use scaling schedules if your workload takes a long time to initialize and you want to scale out in advance of anticipated load spikes. Now let's take a look at how to implement scaling based on schedule. Once again, we go to Instance Groups and select an instance group. From that instance group, we actually select Edit. Here once again, we configure autoscaling. We select Add or Remove Instances to the group. Then we scroll down to Autoscaling Schedule and click Manage. Then we create a schedule. Give it a name, minimum instance, start time, select time zone, duration, 5 hours, every week, and the days of the week that we want to implement. And say OK. Then we select Save. And last, we'll take a look at scales based on monitoring metrics. When you autoscale a MIG based on the metrics, the autoscaler creates VMs when the metric value increases and deletes VMs when the value decreases. For example, you can define how many VMs you need per user count, latency, or the number of messages in a pub sub subscription. You can use either the built-in metrics provided by the monitoring service or custom metrics that you export from your application. Now let's take a look at how we implement scales based on monitoring metrics. Once again, we start at instance groups. We select an instance group. Then we select Edit. Scroll down to Autoscaling. Turn on Autoscaling. Next, we select Add a Signal. Here we select the signal type, Cloud Monitoring Metrics. Next, we would select Configure. Then you would select a metric. In this instance, you would select VM Instance. Here's a list of the different objects we can implement in our metrics. If you select Instance, then you see you have 29 metrics. Disk usage, apply. Here we can implement the metrics according to the numbers that basically work with our application. So we would select metric target options for auto scaling. And last, we would save. In this demonstration, we've explored the powerful capabilities of the Google Cloud Platform for automating the scaling of resources to meet dynamic workloads. By leveraging GCP autoscaling tools, such as the Compute Engine Management Instance Group, we have shown you how to seamlessly adjust computing resources in response to varying demand. These tools ensure high availability, performance, and cost efficiency by automatically scaling instances based on predefined metrics or custom policies. This automatic approach not only simplifies resource management, but also enhances the overall resilience and adaptability of your applications. With GCP autoscaling features, you can confidently handle traffic spikes, optimize resource utilization, and maintain a consistent user experience, making it an indispensable part of your cloud infrastructure strategy. We discussed the concept of SLIs in the Applying Site Reliability Engineering Practices course. Here's a quick recap. When identifying key SLIs for cloud services, it is crucial to consider metrics that directly reflect the service's performance, availability, and reliability. SLIs are quantitative measurements representing specific aspects of a service performance, playing a vital role in defining and monitoring SLOs and SLAs. When identifying SLIs, start with your users. Consider what aspects your users care about most when using your services, such as speed, availability, accuracy, or other factors. Understanding users' expectations and needs is the first step in identifying relevant SLIs. Choose measurable metrics. For each aspect that users care about, find a way to measure it. Common SLIs include availability, latency, error rate, throughput, saturation, and correctness. Prioritize the most important SLIs. Focus on the SLIs that have the biggest impact on your user's experience and your business goals. Identify which metrics are most critical for ensuring a positive user experience and achieving business objectives. Collect the right data. Set up monitoring tools to gather the data needed to calculate your SLIs. This might involve instrumenting your code to capture relevant metrics, collecting logs, or using third-party monitoring services. Ensure you have accurate and reliable data collection mechanisms in place. And last, aggregate and analyze SLIs. Calculate your SLIs and track them over time. Look for trends and patterns to understand how your services are performing. Regularly analyze this data to identify potential issues before they become major problems and to make informed decisions about improving service reliability. Now let's take a look at a few examples. First, let's look at SLIs for an e-commerce website. Some of the concerns could be availability, percentage of time that websites are accessible, latency, time to load product pages, error rate, percentage of failed checkout attempts. Next, we could take a look at SLIs for an online game. Some of the concerns could be latency, ping time or response time for player actions, error rate, number of disconnects or crashes per hour, and throughput, number of concurrent players supported. And last, let's take a look at SLIs for an API service. Concerns here could be availability, percentage of successful API calls, latency, time to process API requests, and error rate, percentage of API calls that return errors. Now let's move on to other important concepts in SRE, starting with feedback loop. There are four areas of discussion as it relates to feedback loop. First, early problem detection. Constantly monitoring key metrics allows feedback loops to catch issues early, preventing significant problems. This enables faster response times and minimizes downtime. For example, monitoring loops can detect increasing error rates before they impact all users. Next, automatic remediation. Control loops can automatically resolve common issues, such as restarting failed processes or scaling resources to meet demand. This reduces the need for manual intervention and speeds up recovery. For instance, if a process crashes, a control loop can automatically restart it. Next, continuous improvement. Adaptation loops evolve based on past incidences to prevent similar problems in the future, leading to a more reliable and resilient system over time. For example, after analyzing several incidences, an adaptation loop might recommend configuration changes to reduce the likelihood of recurrence. And last, performance optimization. Analyzing performance data through feedback loops helps identify bottlenecks and inefficiencies. This information can be used to optimize performance and enhance user experience. For instance, a feedback loop might identify a slow database query and recommend indexing to improve performance. Feedback loops are vital for creating reliable and high-performance online services. They provide mechanisms to detect and respond to issues promptly, enabling early problem detection, automatic remediation, continuous improvement, and performance optimization. These capabilities are essential for maintaining service reliability and user satisfaction. Implementing effective feedback loops involves carefully selecting metrics to monitor, determine appropriate action, and learn from past experiences, thus ensuring the loops are responsive and adaptive to changing conditions. Here's some example scenarios for using feedback loops. First, load balancing. A feedback loop continuously monitors the load on multiple servers and distributes traffic evenly. This prevents any single server from becoming overloaded, ensuring consistent performance and availability. Next, autoscaling. A feedback loop detects when a service is nearing its capacity limits and automatically provisions additional resources to manage the increased demand. This keeps your service responsive, even during traffic spikes. And last, anomaly detection. A feedback loop analyzes system behavior patterns to detect unusual events, such as sudden spikes in error rates or drop in traffic. This helps identify potential problems early, allowing proactive measures to prevent major disruption. Now let's take a look at service lifecycle management models. Service lifecycle management models are structured approaches or frameworks that guide how IT services are managed from their inception to retirement. These models outline the different phases a service goes through, the activities involved in each stage, and best practices for ensuring the service's success. The goal of SLM models is to maximize the value of IT services throughout their lifecycle while minimizing risk and cost. There are various approaches to managing the lifecycle of an IT service, each with its own philosophy, strengths, and weaknesses. The first approach is a waterfall model. This linear sequential model progresses through distinct phases, such as requirement gathering, design, development, testing, and deployment. Each phase must be completed before the next one begins. It emphasizes meticulous planning and documentation up front to minimize changes later in the process. Large government projects with strict regulatory requirements might use the waterfall model due to its emphasis on documentation and predictability. The popular agile model breaks down development into short iterative cycles known as sprints. Each sprint delivers a usable piece of the service, enabling continuous feedback and adaptation. This approach prioritizes flexibility, customer collaboration, and responsiveness to change. Software startups often use Agile to quickly release and iterate with new features based on user feedback. The DevOps model. This integrates development and operation teams to streamline the entire service lifecycle, emphasizing automation, collaboration, and continuous delivery. It aims to achieve faster, more frequent deployments while maintaining high quality and reliability. Many technology companies, such as Amazon and Netflix, use DevOps to deliver software updates multiple times a day. Service oriented architecture. This breaks down a service into smaller, self contained components that communicate through standardized interfaces. It promotes reusability, flexibility, and scalability of individual components. Large enterprise companies might use SOA to modernize their legacy systems and integrate new technologies more easily. Lean model focuses on maximizing customer value while minimizing waste in the development process. It eliminates unnecessary steps, optimizes workflow, and continuously improves processes. Manufacturing companies often use lean principles to streamline their production processes and reduce costs. Information Technology Infrastructure Library, known as ITIL. This is a comprehensive set of best practices for managing IT services throughout their lifecycle. It aligns IT services with business needs, improving service quality and optimizing resource utilization. Large financial institutions might use ITIL to streamline incident management processes, ensure faster resolution of issues, and minimize disruption to critical business operations. Control objectives for information and related technologies, known as COVID. This is a framework for IT governance and management that focuses on aligning IT with business goals, managing risk, and ensuring compliance. It provides a set of control objectives and best practices for managing IT processes and resources effectively. Healthcare organizations might use COVID to ensure the security and privacy of patient data, adhere to regulatory requirements, and minimize the risk of data breaches. Federated IT Service Management is a lightweight standard for IT service management that is designed to be simple, flexible, and adaptive to organizations of all sizes. It provides a streamlined approach to service management, focusing on core processes and activities. A small software development company might adopt FitSM to establish a basic IT service management framework without the overhead of more complex approaches like ITIL. Enhanced Telecom Operation Map. This is a comprehensive framework specifically designed for the telecommunication industry. It outlines business processes and functions for managing telecommunication services, from customer acquisition and network operations to billing. A mobile network operator might use ETOM to standardize their network operation and processes, thereby improving efficiency and reducing time to resolve network issues. And last, business process model and notation. This is a graphical notation used to visualize, model, and document business processes. Business process model and notation provides a standardized way to represent the flow of activities within a process, making it easier to understand and analyze. A company might use BPMN to model their software development lifecycle by mapping out the steps involved in requirement gathering, design, development, testing, and deployment. Let's now take a look at the need for access control and security. There are 5 areas that we will discuss: protecting sensitive information, ensuring data integrity, preventing unauthorized access, enhancing incident response, and maintaining system availability. Protecting sensitive information can include IP addresses, user credentials, configuration details, and other sensitive information. Ensuring that only authorized personnel can access sensitive logs and monitor data helps maintain confidentiality. This prevents sensitive information from being exposed to malicious actors or unauthorized users within the organization. Unauthorized access to monitor and logging systems can result in tampering with logs, either to hide malicious activities or to manipulate data. Implementing strict access controls helps ensure that logs remain accurate and trustworthy, preserving their integrity for forensic analysis and compliance purposes. Implementing RBAC ensures that users have access only to the information and systems necessary for their role. For example, a system administrator might have access to infrastructure logs, while a developer might only access application-specific logs. This principle of least privilege reduces the risk of insider threats and limits the potential damage from compromised accounts. Requiring MFA for accessing, monitoring, and logging systems adds an additional layer of security. MFA significantly enhances security by reducing the risk of unauthorized access. Secure and controlled access to monitoring and logging data enables security teams to detect and respond to incidences more effectively. They can quickly identify unauthorized access attempts or anomalies that indicate potential security breaches. In the event of a security incident, having a clear, tamper-proof log trail is crucial for forensic analysis. It allows security teams to trace the action of attackers, understanding the scope of the breach and determining how the incident occurred. Too many users querying the system simultaneously can lead to an overload. Access controls help manage user load and ensure that the system remains responsive. Ensuring that only authorized users can perform resource-intensive queries helps maintain the availability and performance of the monitoring and logging infrastructure. For example, let's say your organization is using cloud logging to store logs from a sensitive application. You can use IAM to define a custom role that allows developers to view only the application logs, but not logs from other applications. Additionally, you can enable MFA for users accessing the cloud logging console and configure alerts to notify your security team of any suspicious log entries. By prioritizing access control and security in your GCP monitoring and logging infrastructure, you protect sensitive data, ensure compliance, and maintain the availability of your critical systems. Let's turn our attention to case study. First, we'll look at SRE for Google Services. As Google Services grew rapidly, they struggled to maintain high reliability while continuing to innovate. The traditional operation approach couldn't scale effectively, leading to frequent outages and slow issue resolution. Two solutions were offered. First, error budgets. By defining acceptable levels of failure, Google balanced the need for innovation with reliability. This allowed for controlled risk-taking and ensured the reliability was not compromised by new feature deployments. Next, automation. Implemented automated monitoring and alerting reduced the manual burden on engineers and improved the speed and accuracy of issue detection and resolution. The result was services became more stable, as error budgets provided clear thresholds for acceptable performance, preventing excessive downtime. Also, automation reduced manual work, allowing engineers to focus on more strategic tasks, leading to quicker and more effective problem solving. Next, let's take a look at SRE for Netflix services. While managing the complexities of a global streaming platform, Netflix faced the challenge of ensuring continuous service availability and reliability, especially during peak times. Two solutions were offered. First, chaos engineering. By intentionally introducing controlled failure, Netflix could test their system's resiliency and identify weaknesses before they caused real-world outages. Next, cross-functional teams. Integrating development and operational skills within SRE teams ensured comprehensive understanding and swift resolution of issues. Regularly testing the system's limits helped preemptively address potential failures and ensure higher reliability. Continuous real-world condition testing guaranteed that the service remained robust and available, even during high-traffic events. Let's summarize the topics that we covered, the principles and key components of SRE, and the role of error budgets in balancing reliability and speed, SLOs, SLAs, and SLIs, and strategies for automating toil and repetitive tasks, the importance of opportunity cost in risk and reliability decisions. Other topics that we summarized, the impact of capacity planning on service reliability, using Google Cloud tools for auto-scaling resources and feedback loops, as well as modeling for managing the services lifecycle, and finally, exploring a culture of learning and blamelessness and case studies of SRE implementation. Coming up next, we take a look at advanced monitoring and incident response. Welcome to Advanced Monitoring and Incident Response. My name is Ron Johnson. In this course, we will describe the setup and configuration of advanced monitoring solutions using cloud monitoring. Explain the process of creating and managing alert policies based on specific service level objectives and service level indicators. Identify the use of cloud logging for collecting and analyzing logs from Google Platform and external sources. Explain the configuration and benefits of VPC flow logs for network monitoring and troubleshooting. Implement log-based metrics for creating custom alerts. Compare the methods for managing and sharing dashboards to improve operational visibility. Assess the integration of cloud monitoring with third-party monitoring tools. Analyze strategies for responding to and mitigating incidents in the cloud environments. Using Google Cloud Managed Service for Prometheus, implement detailed metric collection and alerting. Describe the importance of access control and security in monitoring and logging infrastructure. And identify the steps for efficiently managing incident communications and reducing incidents' impact on users. Cloud monitoring tracks the flow of requests to your website, the performance of your applications, and the health of your systems that support them. It alerts you to unusual activity, performance bottleneck, or potential failures, thus allowing you to take proactive measures to ensure the smooth operation of your infrastructure. In addition, cloud monitoring can measure various metrics like response times, error rates, and resource utilization. This data provides valuable insight into the overall health of your infrastructure, enabling you to optimize performance, improve user experience, and prevent costly disruptions. Let's take a dive into how to configure a robust monitoring setup using Google Cloud Monitoring. First, set up Google Cloud Monitoring. Begin by enabling the Google Cloud Monitoring API with your GCP project. This unlocks the full suite of monitoring capabilities for your cloud resources. Next, perform agent installation where applicable. For certain GCP services or custom workloads, you might need to install the Cloud Monitoring agent. This lightweight agent collects performance data and sends it to cloud monitoring for analysis. Third, define monitoring targets. Leverage the wide array of built-in metrics offered by Google Cloud Monitoring. These metrics cover various GCP services, such as Compute Engine, Cloud Storage, and BigQuery. You can also define custom metrics tailored to your specific needs. Cloud logging seamlessly integrates with cloud monitoring. Collect and analyze logs from your GCP services, virtual machines, and applications to gain insight into operational events and errors. And enable Cloud Trace to follow the path of requests through your GCP-based applications. This helps you identify performance bottlenecks and optimize your application's behavior. Next, configure alerts. Cloud Monitoring Alerting System allows you to set up alerts based on metric thresholds, log entries, or uptime checks. Custom notification channels, such as emails, SMS, mobile app notifications, are used to ensure prompt alerts for critical issues. Build informative dashboards. Create custom dashboards in cloud monitoring to visualize key metrics and logs relevant to your application and infrastructure. Design dashboards that provide a clear view of your system's health and performance. And last, perform advanced configuration. Organize monitor resource into meaningful groups to simplify management and analysis. Utilize uptime checks to monitor the availability of your internet-facing services for various geographic locations. Create custom metrics to track specific aspects of your applications or infrastructure that are not covered by built-in metrics. And last, integrate Google Cloud Monitoring with other GCP services like Cloud Logging, Cloud Trace, and PubSub. You can also leverage third-party integrations to enhance your monitoring capability. Let's take a look at an example as it relates to monitoring a web application. First up is metrics. Request latency is tracked to determine the time taken for web pages to load for a smooth user experience. Error rates are monitored, differentiating between server-side errors and client-side errors for efficient troubleshooting. Resource usage, including CPU, memory, and disk space, are continuously measured to prevent bottlenecks and ensure smooth operation. Logs. Application logs are monitored for error messages and exceptions. They provide valuable insight into potential code issues. Web server access logs are tracked to identify any suspicious activity or unusual traffic patterns, thus bolstering security measures. Alerts. Alerts are set up for scenarios such as high error rates, sluggish response times, or resource depletion to ensure proactive issue resolution. These alerts can be configured to notify your team through various channels like email, SMS, or Slack. This will facilitate swift responses and minimize downtime. And dashboards. A comprehensive dashboard is created to display crucial metrics such as request latency, error rates, and resource use in an easily digestible format. Charts and graphs are included to enhance the visual dashboard, which enables the identification of trends and patterns over time. Informed decision-making and proactive optimization are a result. Now let's take a look at advantages of implementing advanced cloud monitoring. First, proactive problem detection and prevention. Advanced cloud monitoring empowers you to detect anomalies, errors, and potential issues before they escalate into major incidences that impact users. By continuously analyzing metrics, logs, and traces, you can identify early warning signs of performance degradation, resource constraint, or security threats. This proactive approach enables you to address problems at their inception and prevent them from causing service disruption or downtime. Accelerated incident response. When issues inevitably arise, advanced cloud monitoring facilitates swift incident response. Real-time alerts notifies your team promptly when predefined thresholds are breached or unusual events occur. By integrating with communication and collaboration tools, you can streamline incident management workflows, ensure faster resolution times, and minimize the impact on your business operations. Data-driven performance optimization. Cloud monitoring provides a treasure trove of performance data, which helps identify bottlenecks, inefficiencies, and area for improvement. By analyzing resource utilization patterns, request latency trends, and error distributions, you can pinpoint optimization opportunities. This data-driven approach enables you to fine-tune your applications, optimize infrastructure configurations, and ultimately enhance the overall performance and user experience. Enhance service reliability and availability. Cloud monitoring plays a pivotal role in ensuring the reliability and availability of your cloud-based services. By continuously monitoring the health and performance of your infrastructure, applications, and dependencies, you can proactively address potential issues before they lead to service disruptions. Additional cloud monitoring enables you to track service level agreements, maintain compliance with uptime guarantees, and foster trust with your customers and users. Here are some key considerations for successfully implementing cloud monitoring. First, cost management. As your cloud infrastructure scales, so do your requirements for monitoring. It's crucial to establish a comprehensive cost management strategy to avoid unexpected expenses. Leverage tools like budget alerts and recommendations for resource optimization to control your monitoring cost effectively. Mitigation of alert fatigue. An overabundance of alerts can overwhelm your team and lead to alert fatigue, where critical notifications are overlooked. To combat this situation, carefully calibrate your alerting thresholds. Prioritize alerts based on severity and impact, and streamline notification channels to ensure that only actionable alerts reach the relevant team members. And last, robust data security. Cloud monitoring involves the collection and analysis of sensitive data related to your infrastructure, application, and potential user activity. It's imperative to implement stringent security measures to protect the data from unauthorized access, breaches, and misuse. And finally, adhere to industry best practices, such as encryption, access control, and regular audits to safeguard your monitoring data and comply with relevant regulations. Previously, we've discussed SLOs and SLIs. Now let's take a look at creating and managing SLO/SLI-based alerts. First, define your SLOs. Start by setting clear objectives for service performance. For example, 99.9% uptime or average response time under 200 milliseconds. Each SLO will have a corresponding SLI, the metrics you'll actually measure. For example, uptime percentage or response time. Choose your alerting tool. You can use your cloud provider's monitoring service like Google Cloud Monitoring or AWS CloudWatch, or other third-party tools. Make sure the tool can integrate with your monitoring data and send notifications, for example, email or SMS. Set thresholds and conditions. Decide when you want to be alerted. This could be when an SLI goes above or below a certain threshold. For example, an error rate exceeds 5%, or when a certain percentage of your error budget is consumed. For example, 50% in a week. When a specific combination of conditions occurs. For example, high error rates and slow response times. Create alerting rules. In your alerting tool, create rules that define the conditions for triggering an alert. Specify the severity of the alert, for example, warning or critical, so that you can prioritize your response. Set up notification channels to ensure the right people are notified when an alert is triggered. Finally, test and refine. Don't just set and forget your alerts. Test them to make sure they're working as expected. Refine the thresholds and conditions over time to avoid false alarms, and ensure you're only alerted when it truly matters. Consider using a multi-window, multi-burn rate approach for more nuanced alerting. In site reliability engineering, it's crucial to strike a balance between timely alerts for critical issues and avoiding unnecessary notifications for transient glitches. Google Cloud Monitoring offers a sophisticated alerting technique called multi-window, multi-burn rate alerting to achieve this balance. Multi-window, multi-burn rate alerting significantly reduces the number of false positive alerts. Transient issues that resolve quickly within a short window won't trigger unnecessary notifications. By considering multiple time windows and burn rates, MWMB alerting helps prioritize alerts based on the severity and duration of an issue. This allows your team to focus on problems that have a greater impact on your SLOs. MWMB alerting enables you to monitor your SLOs more efficiently and ensure that you are meeting your reliability goals. By detecting and addressing issues promptly, you can minimize the risk of violating your SLOs and maintain high service availability. Instead of relying on a single time window and error budget burn rate, MWMB alerting utilizes multiple windows and burn rates to assess the health of your service level objectives. For instance, you might have the following configuration. Short window is a 5-minute window with a high burn rate threshold. This window is sensitive to sudden spikes in errors or latency, indicating problems requiring immediate attention. Medium window is a 30-minute window with a moderate burn rate threshold. This window helps identify issues that persist for a longer duration, but might not be severe enough to trigger an alert in the short window. And long window is a 1-hour window with a low burn rate threshold. This window is designed to detect sustained issues that could have a significant impact on your SLO over time. Now let's take a look at an example of alerting on high error rates. In Google Cloud Monitoring, you'll create an alerting policy to proactively direct and notify you when the API error rate exceeds acceptable thresholds. The policy will consist of 2 alerting rules. The first rule is warning alert. The condition would be that the SLI percentage of successful API requests falls below 99%. Time window would be 5 minutes, and the notification channel would be email, SMS, or designated communication channel. This rule is designed to alert you about short-term fluctuations in the error rate. It serves as an early warning sign, allowing you to investigate potential issues before they escalate. Next would be critical alert. Condition would be the SLI falls below 98%. The time window is 30 minutes, and the notification channel is email, SMS, pager duty, or other high-priority communication channels. This rule signifies a more severe and sustained issue. The error rate has remained below the acceptable threshold for a longer duration, indicating a potential outage or significant performance degradation. Let's now turn our attention to managing alerts in Google Cloud Monitoring efficiently. First up is documenting. Maintain a detailed record of all your alerting policies, including the metric or logs being monitored, the triggering conditions, the notification channels used, and the rationale behind the specific configuration choices. Explain why a particular metric is important, why specific thresholds were chosen, and how the alert relates to your overall SLOs. Clear documentation helps new team members understand the alerting system quickly, facilitates collaboration, and prevents confusion during incident response. Next, reviewing and updating. Periodically review your alerts to assess their effectiveness. Analyze whether they are triggering at the right times and providing actionable insights. Fine-tune alerting thresholds based on historical data and operational experience. Adjust them to reduce false positives and false negatives. Modify alert conditions as your infrastructure evolves or your monitoring requirements change. Add new alerts for newly deployed services or remove outdated alerts for decommissioned resources. And last, automating a response where possible. For example, you could configure cloud monitoring to automatically restart a virtual machine if it becomes unresponsive, or scale up a service if it's experiencing high traffic. Leverage Google Cloud's automation tools, such as Cloud Functions or Cloud Run. Do this in order to execute custom remediation actions based on alerts. This can significantly reduce the manual effort required for incident response. Automating responses can accelerate incident resolutions, minimize downtime, and reduce the burden on your operations team. Let's take a look at considerations for effective alert management. First, prioritize alerts. Classify alerts based on severity and urgency. Ensure that critical alerts receive immediate attention, while less urgent alerts are addressed in due course. Aggregate alerts. If you have multiple alerts related to the same underlying issue, consider aggregating them to avoid overwhelming your team with redundant notifications. Monitoring alert trends. Analyze alert trends over time to identify recurring problems or areas of improvement in your system's reliability. And leverage integration with alerting platforms. Integrate cloud monitoring with incident management platforms, such as PagerDuty or OpsGenie. This is to streamline alert routing and escalation processes. By proactively managing your alerts in Google Cloud Monitoring, you can maintain a high level of service availability, optimize your incident response capabilities, and ensure a smooth and reliable experience for your users. Let's turn our attention to cloud logging. Cloud logging is a powerful tool that can help you gain valuable insight into your systems and improve their reliability, security, and performance. By collecting, storing, and analyzing logs from a wide range of sources, you can make better decisions, troubleshoot problems faster, and build a more resilient infrastructure. Cloud logging automatically grabs logs from various GCP services like Compute Engine, App Engine, and Cloud Storage. It's like having a built-in scribe for your Google Cloud projects. Your logs are stored in special containers called log buckets. You can create different buckets for different purposes. For example, one bucket for application logs and another bucket for system logs. Log Explorer is the main interface where you can view and search your logs. It's like a powerful search engine for your system history. You can filter logs based on various criteria, such as time, severity, source, and use query language to find specific events or patterns. You can create visualizations, charts, and graphs to see trends and patterns in your logs. This helps you to understand how your systems are behaving over time. You can create metrics based on your logs. For example, the number of errors in a certain time period. Alerting policies set up rules that trigger alerts when these metrics exceed certain thresholds. There are two categories of logs from GPC services. First, there's default logs. GCP services like Compute Engine, App Engine, and Cloud Functions automatically send logs to Cloud Logging. You can view these logs in the Cloud Logging console. Then there's custom logs. If your application generates custom logs, you can use the Cloud Logging client libraries to send these logs to Cloud Logging. Let's take a closer look at custom logs. In this example, the code will enable your Python application running on GCP or elsewhere to send structured log messages to Cloud Logging. These custom logs are then stored, indexed, and searched within the Cloud Logging services, making them valuable for troubleshooting, analysis, and monitoring your application's behavior. Let's look at each line of code. This line imports the necessary library, google.cloud.logging, to interact with Google Cloud Logging from your Python code. This creates a logging client object, which establishes a connection to the Cloud Logging API. Here, you obtain a logger object associated with a specific log name, my log in this case. This log name helps you organize and differentiate logs within Cloud Logging. And last, this is where the actual logging happens. The log text method sends a log entry containing the text. This is a custom log entry to Cloud Logging. This entry will be associated with the my log name. There are two ways to collect logs from external resources. First, if you're running applications from outside GCP, use the logging agent to send logs to Cloud Logging. Ensure the agent is properly configured to forward logs from your external system. External applications can also use the Cloud Logging API to send log entries. This is useful for non-GCP environments or hybrid cloud setups. Once logs have been collected, you can then analyze the logs in Cloud Logging. First, you would need to access the logs. Go to the Google Cloud Console and navigate to the Logging section. Use the Log Explorer to search and filter logs based on criteria, such as timestamps, log levels, and specific log fields. You would then move toward creating log-based metrics. In the Cloud Logging Console, you can create log-based metrics to monitor specific events or conditions in your logs. For example, you can create a metrics to count the number of error logs over time. Then you would set up alerts. Use log-based metrics to create alerting policy. You're notified when certain conditions are met, such as a spike in error logs. And finally, you would visualize the logs. Integrate Cloud Logging with other GCP tools like Cloud Monitoring and BigQuery for advanced analysis and visualization. And most importantly, manage and maintain logs. Cloud Logging automatically retains logs for 30 days. You can adjust the retention period based on your needs. Use Log Sync to export and store logs in other GCP services, such as cloud storage for longer retention. Use Identity and Access Management to control who can view and manage logs. Set up roles and permissions to ensure security and compliance. And finally, manage cost and storage. Filter out unnecessary logs. Configure the logging agent and use exclusion filters in Cloud Logging to reduce the log volume. VPC flow logs are a GCP feature that captures information about the IP traffic going to and from network interfaces in your VPC. This data is crucial for monitoring network performance, understanding traffic patterns, and troubleshooting network issues. Each flow log entry captures details like source and destination, ports, protocols, traffic volume, and acceptance status. Here are the steps to configuring VCP flow logs. Go to your cloud provider's console and enable flow logs for the VPCs, subnets, or specific network interfaces you want to monitor. Decide where you want to store your flow logs. Options usually include Amazon S3 or Google Storage Cloud. You could also send them to a log analyst service, such as Amazon CloudWatch Logs or Google Cloud Logging. Choose the format for your flow logs, for example, AWS default format or custom format. And finally, you can filter the logs to capture only specific types of traffic, for example, only traffic accepted by your security groups. Benefits of VPC flow logs in GCP include network visibility. VCP flow logs provide an in-depth granular view of network traffic within GCP. They capture detailed information about every network connection, allowing you to see exactly how data flows between your virtual machines, load balancers, and other GCP resources. This visibility enables you to identify communication patterns, detect anomalies, and pinpoint bottlenecks. Flow logs are also used with troubleshooting. When network issues arise, VPC flow logs become your invaluable troubleshooting companion. By examining the logs, you can trace packet flows, diagnose connectivity issues, and analyze security incidences. Logs can help you with security analysis. VPC flow logs play a crucial role in bolstering the security posture of your GCP environment. They enable you to detect unauthorized access, uncover suspicious traffic, and identify potential vulnerabilities. Compliance. Many industry and regulatory frameworks require organizations to maintain detailed logs of their network activity. VPC flow logs provide a comprehensive record of all traffic that flows within your GCP environment. This can be particularly important for organizations operating in regulated sectors such as finance, healthcare, or government. Logs can help with effective capacity planning. Understanding your network traffic patterns is essential for effective capacity planning. VPC flow logs provide valuable data to forecast future growth, optimize resource allocation, and right-size infrastructure. And finally, cost optimization. VPC flow logs not only help you understand your network traffic, but also empower you to optimize it. By analyzing the logs, you can identify unnecessary traffic, eliminate inefficiencies, and improve resource utilization. Here's some examples of what can be captured by a VPC flow logs. A user reports they can't access your website. You can use flow logs to see if their traffic is being blocked by a security group or if there's a network routing issue. You notice a sudden spike in traffic from an unknown source. Flow logs can help you determine the nature of the traffic and whether it's a malicious attack. You want to understand how users are interacting with your application. Flow logs can show you which features are most popular and how much bandwidth different services are using.
In this topic, we are going to talk about the implementation of log-based metrics and their uses in creating custom alerts. Now, this topic specifically focuses on creating custom metrics from your application logs and then uses them to trigger alerts when specific condition arises. There are certain prerequisites as usual. So there is Google Cloud project that you need and it needs to be active. And you have to have something running in the background. Maybe it could be a virtual machine instance or an application that would generate logs. Now, we are on the Google Cloud console. So from here, what I'm going to do is I'm going to search for logging, and from the search results, I'm going to click on this option called Log Explorer. It is already showing some bit of graphs. It is trying to load some graphs, and then there are certain timeline it is focused on. Now, if I simply go down to an option called log-based metrics, let me just scroll up, and from log-based metrics, I select this option. Now, I can create a specific metric and I already have three of them. Now, the issue here is that if you create a metric right away and trying to create a custom policy and use that metric, it is not going to be visible immediately. So it's going to take some time, maybe a few hours as well. I have already created this one and it is called error count and it is going to be available. I'm going to walk you through how to create a custom policy and then we can see if this error count is able to track any errors. What I'm going to do is I'm going to just walk you through how to create a metric but still proceed with error underscore count. It is a counter that is the default option. You have to give it a name that is mandatory. You can't skip that. And project logs is the default option and you can build the filter. So for example, I can put it as severity is equal to error. All right. So I'm going to put that as a filter or I can just leave it as blank. It is not mandatory for you to have a filter here. And then I just need to click create metric. I'm going to just go ahead and cancel this one out. Yeah, discard and then we are going to basically use this error count. Now, if I want to see the logs for this particular metric, I need to click these three dots and select option called view logs for metric. And I get only errors. Notice that severity is equal to error. I can change this. What if I just type info and I run this query again and the errors will not be shown? It would be only the info events that will be shown. Now, what if I want to see warning and run the query? I get to see only the warnings. But if I go ahead and delete this and run the query again, I should be able to see everything. So notice this default info, notice error warning, all these are displayed. This is a huge log. I need to scroll back up and it will try to keep refreshing this depending on the time soon. If I just go ahead and click on this, it shows me that this particular time there were 4 debugging events. There were 132 info events. There were 26, warning 5 and error 6. Now I can simply go ahead and see this. Now we have done this. Next thing we need to do is create a custom alert. Now to be able to do that, we need to head over to monitoring. I already have that opened up in another tab. And for this, what we need to do is create a policy, and I click on this option called create policy. I already have 3 of them, by the way, created, and I am just going to walk you through this how to create a policy. But we'll go ahead and use one of the existing ones. I need to select a matrix. Now I just type my metric name error. I just leave it at this and it filters that. Now this is a virtual machine instance metric. So I'm going to go ahead and click on VM instance and then select this option called log based metrics and this error underscore count, and it is logging.googleapis.com/users. This is the metric that I need to select. Once I select this, I need to click on apply so it gets selected here. If I want to add a filter, I can add a filter again. I can just simply say severity is, for example, I would say project ID is equal to SKS001 and done. Now this is the filter that I have added, so I can just click on next. Then I need to define the threshold value, say 1, and we just keep everything as is. Condition name is again error underscore count. I click on next and then I need to select notification channel. I'm going to select pub sub, which I had created earlier and which is called PS. I'm going to go ahead and select that notify on incident closure, which is 30 minutes. Severity is, I want to say, okay, error is the severity, and I'm going to name a policy. So I'm going to name it as SKS underscore errors. I click on next and I go ahead. Right now, it is not displaying any data because there are no errors generated. I'm going to just go ahead and click create policy. All right, so this is created. Now, if I want to go back and see all the policies that I have, I need to click on this option called alerting, and it shows me the number of policies that I have. So initially it was 3, now it is 4. I just click on view all and SKS errors is what we created. If I click on these 3 dots, I can edit, copy, delete this policy. I'm going to just go ahead and click on this particular policy. Right now, there are no data because there are no errors generated. But this is the way you can create it. But do remember that if you create a metric, give it some time before it is available for policy to use. A lot of time, it may take several hours before the metric is available. For me, it took more than 30 minutes for it to be available. So you have to be very cautious. You need to give it some time. Now, the reason you would need to create the log matrix is because it will help you track custom events from your logs, which could be your application logs. You can also set up alerts to be notified when specific conditions are met, helping you proactively address the issue. Now, just to recap in this particular topic, what we did was we saw how to create a particular log-based metrics, even though we did not create one, but we just walked through the process and learn how to do it. And then we use the existing log based metric, which was called error underscore count, and we used it in one of the new policies in monitoring that we created.
Now let's discuss dashboards. Dashboards are a very valuable way to present information in a consolidated format. For managers, it saves time and effort to check your environment status. Here's a chart that represents pros and cons for using and sharing dashboards. Here we list in-house solutions, cloud-based monitoring platforms, open source monitoring tools, and hybrid approaches. Dashboards have sharing options. Static sharing involves capturing a snapshot of a dashboard at a specific point in time and sharing it as an image or a report. While static sharing is simple and straightforward, it doesn't provide real-time updates or allow interaction with the data. Live sharing enables users to view and interact with real-time data through shared links, embedded dashboards, or displays. This method promotes collaboration and transparency, but may require authentication or access controls to protect sensitive data. Here we have in-house solutions, cloud-based monitoring platforms, open source monitoring tools, and a hybrid approach. Now let's turn our attention to integration of cloud monitoring with third-party tools. If you already use monitoring tools like Datadog, New Relic, or Nagios, integrating them with cloud monitoring allows you to leverage your existing investment. This provides a unified view without starting from scratch. Cloud monitoring may not meet all your monitoring needs. For example, you might require specialized tools for application performance monitoring, network monitoring, or security monitoring. Integrating allows you to utilize the best features of each tool. And when an alert is triggered, it's crucial to notify the right people quickly. Integrating cloud monitoring with incident management tools like PagerDuty streamlines this process and ensures timely responses. Next, let's take a look at how integration works. First, there's data export. Cloud monitoring can export its metrics, logs, and alerts to other tools. This might involve using APIs, agents, or pre-built integration. Next, there's data import. Some tools can send their data to cloud monitoring. This is useful if you want to centralize your monitoring data. You then can take advantage of cloud monitoring dashboards and alerting capabilities. Next, there's alerting and notification. You can set up alerts in cloud monitoring that trigger notification in other tools like PagerDuty or Slack. Setting up alerts ensures that the right people are notified about critical issues. And finally, unified dashboards. Some platforms allow you to create dashboards that combine data from cloud monitoring and other tools. This gives you a single view of the health and performance of your entire system. Benefits of integration include comprehensive monitoring. Attain a broader view of your system by combining data from multiple sources. Specialized insights. Leverage the strength of different tools for different monitoring needs. Streamline workflow. Automate incident response and reduce manual effort. Simplified management. Centralize your monitoring data and configuration in one place. Methods of integration include API integration. Cloud monitoring provides APIs that allow organizations to programmatically access monitoring data. Third-party tools can integrate with these APIs to pull data from cloud monitoring and incorporate it into their own dashboards and reporting systems. Webhooks and alerts. Cloud monitoring can trigger webhooks and alerts based on predefined conditions and thresholds. Organizations can configure cloud monitoring to send alerts to third-party tools, which can then process the alerts and take appropriate action. Data export. Cloud monitoring supports the export of monitoring data to external systems, such as Google Cloud Storage or BigQuery. Organizations can export data to these systems and then use third-party tools to analyze and visualize the data. And service integration. Some third-party monitoring tools offer built-in integration with cloud monitoring. Integration streamlines the setup process and enables organizations to quickly leverage cloud monitoring data within their existing monitoring workflows. There are some important considerations for integration. When integrating cloud monitoring and other tools, it's essential to consider the associated cost. By thoroughly assessing these factors and planning accordingly, you can build a more powerful and comprehensive monitoring system. Integrating multiple monitoring tools can significantly impact your overall cost. This would include operational cost, personal cost, licensing and subscription fees, and there's always hidden cost. Be sure to factor these costs into your budget and conduct a thorough cost benefit analysis to ensure the integration provides value. Integrating multiple monitoring tools can increase the complexity of your monitoring setup in several ways. These would include configuration and setup, maintenance and updates, data integration, security compliance, and user training. It's crucial to have a well-defined strategy and sufficient resources to manage this complexity. This includes having dedicated personnel or teams responsible for overseeing the integration and ongoing maintenance. Ensuring data compatibility is critical for the seamless integration of multiple monitoring tools. Focus on data formats, schemas and metadata, timestamps and time zone handling, normalization, data fidelity and granularity, and last, integration of APIs. Ensuring data compatibility requires careful planning and often requires custom development work. Investing in robust ETL processes and having a clear data governance strategy can help address these considerations and overcome challenges in integration. Let's review key strategies for incident response and mitigation. Develop a comprehensive incident response plan that outlines roles, responsibilities, and step-by-step procedures for various types of incidents. This plan should include communication protocols to ensure everyone involved knows how to react and who to notify. Conduct regular drills and training sessions to ensure all team members are familiar with the incident response plan. Continuously monitor systems health using metrics, logs, and alerts. GCP's cloud monitoring and cloud logging provide comprehensive insight into systems performance and potential issues. Set up automated alerts for key metrics and events. Establish an on-call rotation to ensure that the team members are always available to respond to alerts. Quickly assess the scope and impact of the incident. Use tools like GCP error reporting and Stackdriver Trace to collect relevant data and error messages. Assess the severity of the incident to determine the urgency and resources required. Identify the root cause by analyzing logs, metrics, and traces. Take immediate action to limit the impact, such as restarting affected services, rolling back recent changes, or isolating compromised components. GCP's Cloud Deployment Manager can help manage configurations and rollbacks. Implement temporary solutions to maintain service continuity while the underlying issue is being resolved. Keep all stakeholders informed about the status of the incident and expected resolution times. Once the root cause is identified, apply a permanent fix. Ensure thorough testing before deployment to avoid recurrence. Monitor the system's post-fix to confirm that the issue is resolved and stability is restored. Gradually bring services back online, ensuring continuous monitoring to detect any anomalies. Conduct a detailed post-mortem analysis to understand what went well and what didn't, and how similar incidences can be prevented in the future. Document findings and share them with the team. Create and prioritize a list of action items derived from the post-mortem. Here are a few cloud challenges in incident response and strategies. Cloud environments, especially those leveraging microservices, are inherently complex and distributed. Use GCP Service Mesh and Istio for better visibility and control across services. Ensure clear delineation of responsibilities between your team and Google Cloud for different aspects of incident response. Automate routine tasks within the incident response process using GCP's cloud functions, Cloud Run, and automated scripts to reduce manual effort and speed up recovery. Adopt immutable infrastructure practices, where services and instances are replaced rather than modified. This can be managed using GCP's Cloud Build and Container Registry to deploy consistent, version-controlled infrastructure. Now let's take a deeper look at postmortems. Postmortems, sometimes referred to as retrospective analysis or incident reviews, are a structured and thorough examination of an incident or outage that has already occurred. The primary goal of a postmortem is not to assign blame, but to gain a deep understanding of the event, identify its root causes, and derive valuable lessons to prevent similar incidents in the future. Let's take a look at some key components of a postmortem. Creating a detailed timeline of events leading up to and during the incident. This involves collecting data from various sources, such as logs, monitoring tools, and eyewitness accounts. This is to establish a clear sequence of events. Conducting a rigorous investigation to determine the fundamental reasons behind the incident. RCA techniques like the 5 whys or fishbone diagrams are often employed to drill down to the underlying causes rather than just focusing on the symptoms. Evaluating the extent of the impact caused by the incident. This includes quantifying financial losses, downtime, customer dissatisfaction, and any other relevant consequences. Identifying key takeaways from the incident. This may involve technical insights, process improvements, communication gaps, or training needs. Developing specific, actionable recommendations to prevent or mitigate similar incidents in the future. These recommendations should be prioritized based on their potential impact and feasibility. And documenting the entire postmortem process, including findings, recommendations, and action plans. This documentation should be shared with relevant stakeholders. This is to ensure transparency and accountability. Here we will look at an example of a postmortem of a website outage. Imagine a scenario where an e-commerce website experienced a major outage due to a database failure. A postmortem would involve the following steps: gathering logs and metrics to determine the exact time the outage started, when the database failed, and how long it took to recover. Investigate why the database failed, whether it was due to hardware failure, software bugs, or misconfiguration. Quantify the financial losses due to lost sales, customer churn, and potential damage to brand reputation. Identifying weaknesses in the database redundancy and failover mechanisms, and gaps in monitoring and alerting systems. Implementing a more robust database backup and disaster recovery strategy. Enhancing monitoring and alerting, and conducting regular database health checks. Thoroughly documenting the entire postmortem process, including the timeline, root causes, impact assessments, lessons learned, and recommendations. This documentation should be clear, concise, and easily accessible to all relevant stakeholders. The postmortem findings should be shared with all relevant teams and stakeholders, including engineering, operations, customer support, and management. This communication should be transparent, highlighting both the success and failure of the incident response, and emphasizing the actionable recommendations to prevent further outages. Postmortems contribute to continuous improvement. By analyzing incidents in details, organizations can learn from their mistakes and avoid repeating them in the future. Postmortems help identify root causes and systemic weaknesses that may have contributed to the incident. They enable organizations to proactively identify and address potential risk and vulnerabilities before they escalate into major incidents. By implementing preventive measures based on postmortem findings, organizations can reduce the likelihood of future incidents. By identifying gaps of inefficiencies in incident response processes, organizations can implement improvements to streamline workflows and enhance their effectiveness. And in conclusion, a blameless postmortem process fosters a culture where mistakes are seen as opportunities for growth and improvement. It promotes a culture of accountability, transparency, and continuous learning within the organization. By openly discussing incidents and sharing insights across teams, organizations foster a culture of collaboration and innovation, thus driving continuous improvement over time.
In this topic, what we are going to do is we are going to set up and use Google Cloud's managed service for Prometheus for detailed metric collection and alerting. Now, One of the prerequisites that you have is you have to have a GKE cluster, which is Google Kubernetes Engine cluster that you need to have. And I have already done that. So you can use this particular command called gcloud container clusters create and then sks dash cluster. You set the zone and number of nodes and the type of machine you're going to use. So this command will create that cluster. So I'm going to just switch over to that particular screen where the cluster is already set up. So here is the screen, which is SKS cluster. Now, when I set it up, what it did was it automatically enabled managed services for Prometheus. So it already did that. So what I did was I went into the properties by clicking on SKS cluster. And from here, I searched for that particular feature, which was called managed service for Prometheus. Right now, it is set to disabled because I had disabled it. But when I created the cluster, this was enabled. So what I'm going to do is I'm going to show you how to enable or disable. You can click on this edit icon and then you can enable it from here. So that is one way of enabling it. And if I just cancel it out, then if I go on to the monitoring tab, so if this is not open, what I need to do is search for monitoring, and from the search result, I can select monitoring. Now, by default, overview tab is selected. So I need to select dashboards. And once I do that, it's going to show me all the dashboards that I can create. So I'm going to click on GKE clusters. Now, notice that there is SKS cluster not detected state. So this is managed Prometheus status. Now what I need to do is I can simply go ahead and click on this, select all and enable, because there is only one of these. So I'm going to just go ahead and click. It will automatically select that. And then it will give us this dialog box where enable managed collection for SKS cluster. Now, here, this is basically enabling managed collection for this particular cluster, and this is going to be using managed service for Prometheus. So I'm going to go ahead and click enable managed collection. Now this is going to take a little while for it to configure, and once this is done, then we'll be able to go ahead and proceed to the next step. So right now it gives us a notification which says enabling managed collection for SKS cluster. Now if I would have just gone here and edited this option managed service for Prometheus and gone on to edit mode, and if I would have selected this, it would have also done the same thing which we have done on this particular tab. So I'm going to go ahead and close this particular notification, and we'll just wait for this to be enabled. So once this is enabled, then the status for managed Prometheus will change and pending will no longer be displayed. So we'll have to just wait for this to take place. All right, so the status has now changed to managed collection, which means now this particular cluster is being managed by Prometheus. So now if I try to select this cluster, I won't be able to do that. Now on the left panel, if I select managed collection, then this is unmarked under that. Now if I go to self-deployed, there is nothing. If I go to not detected, there is nothing. But if I select all, then obviously because it's taking all these three options, so this is there. So now you have enabled Prometheus for this particular cluster. So I'm going to go ahead and close this notification. Now, the next thing is what we are going to do is click on this option called metrics management in the left pane under configure section. So I'm going to go ahead and click on this. And here what we will do is we will see how to configure policies and alerts that we'll be able to do. So let's wait for this page to load. And once it does that, what we need to do is we need to come down to this particular option called Prometheus. So I'm going to select this. And now there are a lot of options that are available. So notice that there is create alert, create chart, which is basically part of the custom dashboard. So for example, if I just go ahead and click on chart, create chart for the first option, then it gives me this particular chart that is there. Now currently there is some bit of data. Now if I just say save to dashboard, then I can just leave the name as is, and then I need to select the dashboard, which I can say SKS001, and I click on save chart. All right, so this is how you create that particular chart. Now if I go to the dashboard, I click on this option called view dashboard, I would be able to see this particular metric over there. Okay, so let this page load, and if I just scroll down, let's see where this is. So there you go. Prometheus container memory RSS, that is gauge for SKS001. So there is that particular graph that has been generated. So this is the chart that we have added to the dashboard. Now if I go back on this page where we had managed it, so what we are going to do is we are going to try to create an alert policy. So we are going to create it for the same metric for which we had enabled the dashboard. So I'm going to click on create alert, and then it is going to show is we're going to just have to select a few parameters. So by default, it has taken the project name or the project ID as the filter, and then under transform data, so within each time series, there is rolling window function. Now I can simply go ahead and create this policy, or I need to click on next. So let's go ahead and click on next and see what it has on the next page. So there is a condition, so we can leave it as new condition. We can leave the default settings as is. I'm going to just go ahead and select all these and click next. Then again, just go ahead with the default setting, and I'm going to give it a name, SKS alert dash policy. So I've named it as SKS dash alert dash policy, and I'm going to go ahead and click next. Some form fields are incorrect, so we have to just go back and see what it says. Okay, notification channel, you will need to specify that. So I'm going to go ahead and select PS, which is pub sub, and then I think we are good to go now. So I'm going to click on next. All right, so I'm going to go ahead and then click create policy. Okay, so it says alert policy SKS dash alert dash policy saved, and that has been done. Now what we need to do is basically we can go ahead and click on this option called view alert policy. So it's loading that, and once it loads, we should be able to see that policy. Okay, because we have taken the default setting, so there is no severity that is defined, and any time series cross threshold, it triggers, and then above threshold value is 0. So basically most of these things we have not defined. So therefore it's going to just use the default values, and that is actually not fruitful. But here in this demonstration, the reason we just did that because it is to show that how a policy, or rather the alert policy, can be created. Now, just to quickly recap in this particular demonstration, what we did was I showed you the command of how to create a cluster, and then we saw how to enable Prometheus within that cluster, or we can go back to the monitoring tab and enable it from there. Once we do that, we come to metrics management, and here what we can create is an alert policy, and we can also create chart which we can add into a dashboard, and we did that for the first metric that was enabled. And what we did was we basically created a chart and added to our existing dashboard, which was SKS001.
Let's now take a look at the need for access control and security. There are 5 areas that we will discuss: protecting sensitive information, ensuring data integrity, preventing unauthorized access, enhancing incident response, and maintaining system availability. Protecting sensitive information can include IP addresses, user credentials, configuration details, and other sensitive information. Ensuring that only authorized personnel can access sensitive logs and monitor data helps maintain confidentiality. This prevents sensitive information from being exposed to malicious actors or unauthorized users within the organization. Unauthorized access to monitor and logging systems can result in tampering with logs, either to hide malicious activities or to manipulate data. Implementing strict access controls helps ensure that logs remain accurate and trustworthy, preserving their integrity for forensic analysis and compliance purposes. Implementing RBAC ensures that users have access only to the information and systems necessary for their role. For example, a system administrator might have access to infrastructure logs, while a developer might only access application-specific logs. This principle of least privilege reduces the risk of insider threats and limits the potential damage from compromised accounts. Requiring MFA for accessing, monitoring, and logging systems adds an additional layer of security. MFA significantly enhances security by reducing the risk of unauthorized access. Secure and controlled access to monitoring and logging data enables security teams to detect and respond to incidences more effectively. They can quickly identify unauthorized access attempts or anomalies that indicate potential security breaches. In the event of a security incident, having a clear, tamper-proof log trail is crucial for forensic analysis. It allows security teams to trace the action of attackers, understanding the scope of the breach and determining how the incident occurred. Too many users querying the system simultaneously can lead to an overload. Access controls help manage user load and ensure that the system remains responsive. Ensuring that only authorized users can perform resource-intensive queries helps maintain the availability and performance of the monitoring and logging infrastructure. For example, let's say your organization is using cloud logging to store logs from a sensitive application. You can use IAM to define a custom role that allows developers to view only the application logs, but not logs from other applications. Additionally, you can enable MFA for users accessing the cloud logging console and configure alerts to notify your security team of any suspicious log entries. By prioritizing access control and security in your GCP monitoring and logging infrastructure, you protect sensitive data, ensure compliance, and maintain the availability of your critical systems. Now let's take a look at a case study. We will focus on Google. As Google services grew rapidly, they struggled to maintain high reliability while continuing to innovate. Their traditional operation approach couldn't scale effectively, leading to frequent outages and slow issue resolution. They applied two solutions. By defining acceptable levels of failure, otherwise known as error budgets, Google balanced the actual need for innovation with reliability. This allowed for controlled risk-taking and ensured that reliability was not compromised by new feature deployments. Second was automation. Implementing automated monitoring and alerting reduced the manual burden on engineers and improved the speed and accuracy of issue detection and resolution. As an outcome, services became more stable as error budgets provided clear thresholds for acceptable performance, preventing excessive downtime. And automation reduced manual work, allowing engineers to focus on more strategic tasks, leading to quicker and more effective problem solving. Here are steps for efficient incident communication. First, immediate identification and acknowledgement. As soon as an issue is detected by your monitoring tool, acknowledge it immediately. Designate a specific individual or team to lead the incident response and communication efforts. Next, initial communication. Set up targeted notifications, concise information, and realistic expectations. Third is regular updates. This includes consistent communication, transparent information, multi-channel approach, and audience-specific messaging. And last, resolution and post-incident communication. This entails detailed explanations and support information. Always focus on reducing incidents' impact on users. Whenever possible, offer temporary workarounds or alternative ways for users to access your service during the incident. Consider providing extensions for deadlines or subscriptions that were impacted by the incident to alleviate user frustration. And last, inform users in advance about planned maintenance or potential issues that could affect their experience. Let's take a look at some tools for effective incident communication in GCP. Maintain dedicated web pages to post real-time updates on the status of services. Tools like GCP Cloud Status Dashboard can be helpful. Use systems to send emails, SMS, or push notifications to large user groups. Utilize platforms like PagerDuty, OpsGenie, or GCP's Incident Response and Management. This will streamline communications and automate incident response workflows. Let's summarize what we've covered in this class. Advanced monitoring solutions using cloud monitoring and cloud logging, alerting policies, VPC flow logs and log-based metrics, methods for managing and sharing dashboards, integration of cloud monitoring with third-party monitoring tools, incident response, mitigation, and postmortems, Google Cloud's managed service for Prometheus, access control, and finally, steps to manage incident communications. Coming up next, we will take a look at performance tuning and cost optimization. Welcome to Performance Tuning and Cost Optimization. My name is Ron Johnson. In this course, we will take a look at identifying techniques for analyzing and improving cloud service performance using Google Cloud's Operations Suite. Describe the applications of Cloud Trace and Cloud Profiler in diagnosing and resolving performance bottlenecks. Use preemptible virtual machines and committed use discounts for cost-effective cloud computing. Describe the process for configuring and using cloud monitoring for performance insights. Outline strategies for sizing and scaling resources based on the demand to optimize performance and cost. Describe the implementation of network tiers and their impact on performance and pricing. Apply cloud functions and Google Kubernetes Engine for efficient resource utilization. Review the considerations for selecting and managing compute resources to reduce cost without sacrificing performance. Analyze case studies focusing on successful cost optimization strategies in Google Cloud Platform. Compare different strategies for monitoring and managing cloud expenditures. Leverage sustained use discounts for cost savings. And highlight the roles of performance testing and optimization in maintaining high service levels while controlling cost. Cloud Profiler identifies performance bottlenecks in your code by analyzing CPU usage and memory allocations. Techniques include profile analysis. Identify performance bottlenecks and understand resource usage patterns, helping to optimize code and reduce resource consumption. Heat maps. Visualize the distribution of CPU and memory usage across different parts of your application. And comparative profiling. Compare profiles over time to identify changes in performance characteristics after deployments or changes in usage patterns. Cloud monitoring collects metrics, events, and metadata to provide a real-time view of your service's health and performance. Here's how you can leverage this tool. Automatically collect metrics from Google Cloud services and external applications. Use custom metrics for more tailored insights. Create custom dashboards to visualize metrics in real time. Share these dashboards across teams for collaborative monitoring. Set up alerting policies that notify you via email, SMS, Slack, or other channels when certain conditions are met. And ensure your applications are available to users by creating uptime checks from multiple geographic locations. Cloud logging aggregates and stores logs from your applications, virtual machines, and other Google Cloud resources, making it easy to search, analyze, and troubleshoot. Key techniques include collecting logs from various sources, including Google Cloud services, VMs, containers, and third-party applications. Use the Cloud Logging Console to filter and analyze logs, helping to identify patterns, errors, and performance issues. Create metrics based on log data to monitor specific events or error rates. Export logs to BigQuery for advanced analysis or to cloud storage for long-term retention. CloudTrace helps understand the latency of your application by tracing requests as they flow through your distributed systems. Techniques include trace requests across multiple services and components to identify bottlenecks and latency issues. Visualize latency distribution and trace individual request paths to pinpoint slowdowns. Adjust sampling rates to balance the granularity of data collection with performance overhead. Cloud Debugger allows you to inspect the state of your running application in real time without stopping or slowing them down. This tool is invaluable for troubleshooting live issues. Key features include snapshots. Capture snapshots of the application state at specific code locations, including local variables, and the call stack. Log points. Dynamically add logging statements to running applications without redeploying them, helping to gather more context around issues. Cloud Profiler identifies performance bottlenecks in your code by analyzing CPU usage and memory allocations. Techniques include profile analysis. Identify performance bottlenecks and understand resource usage patterns, helping to optimize code and reduce resource consumption. Heat maps. Visualize the distribution of CPU and memory usage across different parts of your application. And comparative profiling. Compare profiles over time to identify changes in performance characteristics after deployments or changes in usage patterns. To identify changes in performance characteristics after deployments or changes in usage patterns. Now that we've taken a look at some of the tools in Google Cloud's Operations Suite, we can turn our attention to techniques for analyzing cloud service performance. You can establish a robust monitoring strategy. Identify critical performance metrics that align with your SLAs and SLOs. These might include latency, error rates, throughput, resource utilization, and request rates. Leverage logging for deeper insights. Ensure that your application log events are in a structured format, making it easier to search, filter, and analyze. Create custom metrics in cloud monitoring based on logs. This allows you to track application-specific events and correlate them with other performance data. Trace requests for end-to-end visibility. Instrument your application to send trace data to Cloud Trace, enabling you to follow requests across services and pinpoint where latency is introduced. Analyze trace spans to identify slow operations, bottlenecks, and dependencies between services. Utilize debugging and profiling tools. Capture snapshots of your running applications to inspect variables, call stacks, and the overall state at a specific point in time. We can now take a look at techniques for improving cloud service performance. Optimization based on analysis. Use insights gained from monitoring, logging, tracing, and profiling to pinpoint the root causes of performance issues. Capacity planning and auto-scaling. Analyze historical data to predict future usage patterns and ensure you have sufficient resources to meet demand. Caching and content delivery networks. Implement caching mechanisms to store frequently accessed data closer to the users, reducing latency and improving response times. Use CDNs like Cloud CDN to distribute your content across multiple geographically dispersed locations, minimizing latency for users worldwide. Continuous monitoring and improvement. Continuously monitoring your services, analyzing your data, and making incremental improvements to maintain optimal performance. By effectively leveraging these techniques and tools within Google Cloud's Operations Suite, you can ensure that your cloud services remain performant, reliable, and scalable. Performance bottlenecks are sections of code, infrastructure components, or external dependencies that limit the overall speed and efficiency of your application. These bottlenecks can manifest in slow response times, high resource utilization, or even crashes under heavy load. CloudTrace is a distributed tracing system that provides a detailed view of how requests flow through your application, even across multiple services and microservices. Here's how it helps diagnose bottlenecks through data-driven decisions. CloudTrace captures timing information, known as latency data. It does this for each step of a request journey, called a span. You can visualize this data in a timeline, clearly seeing which span takes the longest. This data-driven insight pinpoints the specific operations or services causing slowdowns, enabling you to make informed decisions on where to focus your optimization efforts. CloudTrace automatically maps the relationship between different services involved in processing a request. By analyzing this dependency data, you gain a clear understanding of how latency in one service might impact others downstream. This data-driven understanding is crucial for making informed architectural decisions to improve overall performance. If a request fails, CloudTrace provides data-driven evidence showing where in the request path the error occurred. This accelerates root cause analysis and guides you toward the right fixes. You can filter traces by various criteria. For example, HTTP status code, latency, specific services. You do so to focus on the most relevant data. You can also aggregate trace data to understand overall performance patterns. This data-driven approach helps you to prioritize optimization efforts based on the most impactful areas. Cloud Profiler digs deeper into your application's code to pinpoint performance bottlenecks at a granular level. Here's how it facilitates data-driven decisions. Cloud Profiler samples your application's CPU and memory usage at regular intervals, providing concrete data about resource consumption. This data visualization helps you easily spot hotspots that are candidates for optimization. Cloud Profiler even breaks down CPU and memory usage by individual lines of code within a function. This precise data allows you to pinpoint the exact line of code causing bottlenecks, leading to more targeted and effective optimization. By using the data-driven insights from CloudTrace and Cloud Profiler, you can make informed decisions on how to resolve bottlenecks. Use the latency data from CloudTrace and the resource usage data from Cloud Profiler. This is done to pinpoint the root causes of slowdowns. Analyze the data to understand the relationships between services, identify inefficient algorithms, and detect excessive memory allocations. Use the data to guide your optimization efforts, such as refactoring code, tuning queries, or scaling resources. Continue to collect data and monitor the impact of your optimizations. Use the data to validate the effectiveness of your changes and identify any new bottlenecks that may arise. By emphasizing a data-driven approach throughout the process, you can ensure that your decisions are based on concrete evidence and they lead to more effective performance improvements. Now let's take a look at some cost-effective services. Preemptible VMs are cost-effective types of virtual machine instances available at significantly reduced prices. You can save up to 80% less than regular on-demand instances. The trade-off for this discount is that GCP can terminate these VMs if the resources are needed for other tasks. These VMs can be interrupted and restarted without significant consequences, such as batch job processing, data analysis, media transcoding, and scientific simulations. Applications designed to handle interruptions and distribute workloads across multiple VMs, such as distributed computing frameworks and containerized applications using Kubernetes. Testing new ideas of running experiments where cost is a major factor, such as prototype development, machine learning model training, and temporary environments. Some best practices for preemptible VMs would be to checkpoint your work. Regularly save the state of applications to quickly resume if interrupted. Distribute workloads. Spread tasks across multiple preemptible VMs to minimize the impact of individual interruptions. Combine with autoscaling. Use GCP autoscaling features to automatically replace preemptive VMs with new ones, thus maintaining desired capacity. And monitor usage. Keep an eye on preemptible VM usage to ensure maximum efficiency within budget constraints. Another cost-saving measure is to use committed use discounts. Committed use discounts provide savings of up to 57% on specific VM types in exchange for using them for a set period of 1 to 3 years. Some use cases for committed use discounts would be steady-state workloads, applications with predictable resource requirements that run continuously, such as a web server, databases, and enterprise applications, mission-critical applications, services that cannot tolerate interruptions, such as financial transaction systems, healthcare applications, and critical infrastructure services, long-term projects, projects with a long-term horizon and specific VM requirements, such as large-scale data warehousing, ongoing SaaS applications, and search projects. Here are some considerations for committed use discounts. Commitment period. Ensure the commitment period aligns with your project's timeline and resource needs. Resource type. Choose the VM type that best suits your workload requirements, as CUDs apply to specific VM types. Payment options. GCP offers upfront and monthly payment options for CUDs, providing budget flexibility. We will now look at the process for configuring and using cloud monitoring. Define your monitoring goals. Begin by clearly identifying what you want to monitor. Determine the key performance indicators that are crucial for your specific application and services. Install the monitoring agent. To collect metrics from your compute engine instances and other resources, you need to install the Cloud Monitoring Agent, formerly known as Stackdriver Agent. This agent automatically gathers and sends data to cloud monitoring. Enable and customize metrics collections. Cloud monitoring provides a wide array of pre-configured metrics for various Google Cloud services. Enable the relevant metrics based on your monitoring goals. Create dashboards. Dashboards are your visual command center for monitoring. In cloud monitoring, you can create custom dashboards to display the metrics you care about most. Organize your dashboards logically, using charts, graphs, and other visualizations to make the data easy to understand at a glance. Set up alerts, analyze and interpret data. Don't wait for problems to arise. Be proactive. Configure alerting policies in Cloud Monitor to notify you when specific thresholds are breached. Regularly review your cloud monitoring dashboards and alerts. Look for patterns and trends in the data. Spikes or dips in metrics can indicate potential performance issues. Use the insights gained to identify bottlenecks, troubleshoot problems, and optimize your applications. Create uptime checks. Uptime checks ensures your applications are accessible to users. You can create uptime checks from various locations worldwide, simulating user traffic and verifying that your services are responding as expected. Integrate with other tools. Cloud monitoring seamlessly integrates with other Google Cloud services like Cloud Logging and Cloud Trace. By correlating monitor data with logs and traces, you can gain a deeper understanding of performance issues and their root causes. Continuously monitor and improve. Performance monitoring is not a one-time task. It's an ongoing process. Regularly review and refine your monitoring configurations. As your application evolves, you might need to add new metrics, adjust alert thresholds, or create new dashboards. Configuring and using cloud monitoring can provide invaluable performance insights for your Google Cloud resources. Here are some best practices to ensure you get the most of your cloud monitoring setup. Clearly define monitoring objectives. Establish clear goals for what you want to achieve with monitoring, such as improving response times, reducing error rates, or optimizing resource usage. Effectively install and configure the monitoring agent. Regularly update the monitoring agent to the latest versions to benefit from new features, enhancements, and security patches. Customize metrics collection and design effective dashboards. Activate only the metrics that are relevant to your monitoring goals to avoid unnecessary data collection and cost. Group related metrics together on your dashboards for a clear, logical view of your data. Share dashboards with relevant team members to promote collaboration and unified understanding of system performance. Implement proactive alerting. Configure alert thresholds that are neither too sensitive nor too lenient. They should reflect significant deviations from normal performance. Regularly test your alerting configuration to ensure they trigger correctly and reach the appropriate personnel. Analyze data regularly. Schedule regular reviews of your monitoring data to detect trends, anomalies, and potential issues early. Perform uptime checks. Continuously test service availability to promptly detect and resolve issues. Leverage integration. Integrate cloud monitoring with other Google Cloud tools like Cloud Logging, Cloud Trace, and Cloud Profiler. And finally, continuously improve monitoring. Regularly refine your monitoring setup to adapt to changes in your applications and infrastructure. Keep documentation of your monitoring setup up to date to facilitate onboarding and troubleshooting. Now let's take a look at some strategies for efficiently sizing and scaling your cloud resources to meet demand while optimizing both performance and cost. Start by choosing the right size for your resource based on your typical workload. Don't over-provision your resources. Instead, select the smallest instance type or storage capacity that comfortably handles your average workload. This prevents you from paying for resources you don't regularly use. Use tools like cloud monitoring to continuously monitor your resource utilization, such as CPU, memory, disk, and network. Analyze historical data to understand usage patterns and peak demand periods. This data will help you make informed decisions about when and how to scale. Implement auto-scaling to dynamically adjust your resources based on demand. Auto-scaling policies can automatically add or remove instances based on predefined metrics like CPU utilization or request rates. This ensures optimal performance during peak times and cost savings during low demand periods. Use load balancers to distribute incoming traffic across multiple instances of your application or service. This prevents any single instance from becoming overwhelmed and ensures a smooth user experience even during traffic spikes. And if you have predictable traffic patterns, consider scheduled scaling. You can schedule instances to start or stop based on known peak or off-peak hours. This is a simple way to optimize cost without sacrificing performance. Now let's take a look at some strategies for sizing and scaling resources. Spot instances are compute capacity that is available at a significant discount compared to on-demand pricing. They are ideal for fault-tolerant workloads that can handle interruptions, as they can be preempted with short notice. If your application relies heavily on a database, optimize its performance to avoid becoming a bottleneck. This can involve indexing, query optimization, caching, and choosing the right database instance type for your workload. Use a content delivery network to cache your traffic content closer to your users. This reduces the load on your origin servers and improves page load times for users across the globe. Regularly review your resource usage and scaling policies. As your application evolves, your needs may change. Make adjustments based on your latest data and insights to ensure you're always getting the best performance and cost efficiency. And leverage cloud cost management tools provided by your cloud provider. These tools can help you track your spending, identify cost optimization opportunities, and set budgets to avoid unexpected bills. Network tiers are different levels of service offered by cloud providers for internet traffic to and from your cloud resources. These tiers offer varying levels of performance and reliability, with corresponding price differences. There are two types of network tiers. First, there's premium tier. This tier routes traffic over the cloud provider's private global network, offering the highest performance and reliability. It's designed for applications that demand the lowest latency and highest availability, but it comes at a higher price. Then there's standard tier. This tier uses a combination of the cloud provider's network and the public internet. It delivers good performance for most applications at a lower cost compared to the premium tier. Here's a comparison of network tiers. Premium tier traffic primarily travels over Google's extensive private fiber network, which is optimized for speed and reliability. This network has a global reach with numerous points of presence worldwide, ensuring consistent performance across regions. Standard tier traffic primarily travels over the public internet, utilizing transit ISPs to reach its destination. While some portions may use Google's network, it involves more hops and is subject to the congestion and variability of the public internet. Premium tier performance offers lower latency, higher throughput, and more consistent performance due to the dedicated, optimized nature of Google's private network. This makes it ideal for real-time applications, gaming, and latency-sensitive workloads. Standard tier performance generally has higher latency, lower throughput, and less predictable performance due to the reliance on the public internet. While suitable for many applications, it might not be the best choice for those requiring the utmost speed and consistency. Premium tier reliability boasts higher reliability due to fewer network hops, reduced congestion, and the robustness of Google's infrastructure. Google also offers a service level agreement for premium tier, guaranteeing a certain level of uptime. Standard tier reliability is lower due to the increased number of network hops and the inherent variability of the public internet. There is no SLA for standard tier. The superior performance and reliability comes at a higher cost due to the investment in and maintenance of Google's private network. Standard tier is more cost effective as it leverages the existing infrastructure of the public internet. Typical use cases for the premium tier environment would include video conferencing, gaming, large-scale data transfers, and mission-critical workloads. Premium tier is well suited for global applications, requiring low latency and high reliability. Standard tier would be suitable for general web applications, development, testing environments, and applications where minor latency variations are acceptable. The choice between network tiers depends on your application's specific requirements. Consider the following factors. If your application demands the lowest possible latency and highest reliability, the premium tier is the way to go. If cost is a major concern and your application can tolerate slightly higher latency, the standard tier is a good choice. Applications that involve real-time interaction, large data transfers, or strict service level agreements usually benefit from the premium tier. You can typically select the network tier when you create your cloud resources in your cloud provider's console.
In this topic, we'll learn how to use Cloud Function and Google Kubernetes Engine or GKE for efficient resource utilization. There are going to be series of commands that we would be running, and some of these commands are time-consuming tasks. I have already executed that. For example, I have already set up the cluster that itself takes around 20 to 25 minutes. There are some of the things that you may not need to do. For example, if you've been using the current project, you may not need to set up another project. Otherwise, you can use command gcloud config set project and give your project name. You need to enable the Kubernetes Engine API if it is not already enabled and create Kubernetes cluster. Now, once you have already done this, then you would need to authenticate with your newly created cluster. Whatever is your login account on your console, it will authenticate with that, and this is the command that you need to use. It is gcloud container clusters get credentials, SKS cluster, and then you need to give the zone name. Now, another critical thing that you need to do is to use the cloud function with GKE that you need to create the deployment and the service. Now, there are two YML files that you are going to be using. I'm going to just walk you through those files, and now you need to open the console. Once you open the console or the Cloud Shell, I just click Open Editor, and there are going to be two files that we are going to be using. Now, what are these two files about? These are two files basically define your application. There is this hello world that is going to be there. Another one is this file called deployment.yml file. This also defines the content for your service. Now, once you have done that, what you need to do is you need to start going ahead and start the rest of the commands. If you don't know the external IP for your cluster, you can use this command. I'm going to just copy this command and head over to this particular place and open the terminal. Now, once I need to do that, I need to simply paste the command, or I can type it out, but pasting is always quicker. I'm going to just go ahead and press enter. Now, I get the external IP address. After this, what I need to do is I need to create a file called main.py with the required code, and this is the function that we need to create. And this is also created. I am going to head back to the editor. I click on Open Editor. Now I click on this file called main.py. This contains the code which returns a message saying hello from simplified cloud function. Now you can have simple code, you could have complicated code. It depends as to what you want to display. But we have just two-liner code, and this is what is going to be executed. Now, once we are done with this, I move over and then I need to now deploy this particular function. To deploy this, I need to again head back to the terminal by clicking Open Terminal. And then I need to simply use this function, which is this function that I had shown, gcloud functions deploy. This is what is going to be deployed, and this trigger hello GKE. Now, before we execute this function, you need to have a look at what this function is all about. What I'm going to do is I'm going to head over to another tab. This is this function that I had created, and you can do this by using create function. And then once I click on this, there are simple series of steps that we need to define. I need to give it a function name, and then for better resource utilization, I configure a lot of things such as runtime, build connection, and security and image repo. I can define a lot of things and also the runtime environment variables. Now, once I am done with this, I can click on next, and this is where I define the code for my function. But since we already have this, what I'm going to do is cancel this out, and we are going to go back to trigger hello GKE, and I'm going to click on this. It already starts to show me the graphs, and these are basic metrics that are there. If I can look at the duration for last 12 hours, if I look at it, it still shows me the same. If I click on one day, then probably I will have some more data to display. So there are more data that appears. Now, what I need to do is I need to click on edit. So it loads the function in edit mode and basically runtime build again those same settings. I can simply click on next, and then I can download the code from the source code, and it is basically in cloud storage. It is in zip format. I can simply go ahead and download this. And now here is what I can do. I can simply deploy this code from here, or I can go ahead and use this command in both ways. I'll still get the same output. Let's go ahead and use this command. We are going to head back to the terminal, and I'm going to go ahead and execute this command. It takes a minute or two to execute this command, and once it is done, then it gives us a URL on which if we click, it will give us the output for this particular file, that is main.py file that we had created, and it had code, so that message string that was there, it will be displayed. Let it run. Next command is get function URL. We'll be able to get the URL from here. I'm just going to go ahead and copy this command and wait for that particular command to finish. It is now deploying the function. That may take a while, up to 2 minutes, or it does take around 2 minutes or so to deploy this function, and it might even take more time if you have a bigger function which has a lots of code that needs to be worked upon. We only had 2 lines of code that needed to be used. Therefore, there was not much that is going to be here. Now it needs to set up the infrastructure in the background. Therefore, it will take a few minutes before it can actually deploy that particular function. And once that function is deployed, we'll get a URL. We click on that URL. We get into a new tab. That is where the content from main.py will be displayed. All right, this is done. There is this HTTPS trigger. This is the URL that is there. But I can also get the URL by executing the command. And what I'm going to do is I'm going to just head back, copy this command and paste it here. Once I do this, I press enter. It will give me the same output in which it will display the deployment URL, and that is it. It also displays the HTTPS trigger. In fact, we actually did not need to execute this command. We could have just taken the output from the previous command, which was deploy command, and we could have used that URL. But it is always good to know that you can use a particular command to get the URL. I just go ahead and click on this particular URL. Once I have done that, it gives me a message, hello from simplified cloud function. That is the output I get. Now, if I go back, open the editor, this is the main.py file where it says hello from the simplified cloud function. Now, there are a lot of things in this context of resource utilization here. Now, once you did not have to set up anything, it was only the cluster that you set up. Rest of the cloud function automatically took care of everything else in the background. Secondly, there is auto scaling. As and when there are more resources required, it is going to auto scale the resources, and it will also add more pods, or it will add more resources in terms of displaying the content that you want to display. And of course, there is less administrative overhead. There are a lot of things that are beneficial when you use cloud functions. Now, just to quickly recap in this particular topic, what we did was we had a cluster, we ran a few commands, we looked through the main.py file, we also looked at deployment.yml file and service.yml file. And then we were able to execute a few commands to generate the URL on which particular main.py will be displayed. And finally, we got to the particular point where we read the message in the new tab that was opened after we clicked on the generated URL.
Let's look at key considerations for selecting and managing compute resources in the cloud to achieve cost savings without compromising on performance. First, right-sizing instances. Don't just pick the biggest and most powerful instance type. Analyze your application's workload to determine its actual resource requirements. Choose an instant type that provides sufficient CPU, memory, and storage to handle your workload comfortably, but avoid excessive capacity that goes unused. Utilize autoscaling. Autoscaling dynamically adjusts the number of instances based on demand. This ensures that you have enough resources to handle peak traffic without over-provisioning during quieter periods. Configure autoscaling policies based on metrics like CPU utilization, request rates, or queue links. Leverage spot instances. Spot instances offer significant discounts compared to on-demand instances, but can be interrupted with short notice. Use spot instances for fault-tolerant workloads that can handle interruptions, such as batch processing jobs, test environments, or distributed workloads that can be quickly restarted on another instance. Consider preemptible VMs. Preemptible VMs are similar to spot instances, offering substantial cost savings in exchange for the possibility of preemption. They are suitable for workloads that can tolerate interruptions and are not time sensitive. Optimize reserve instances. Reserve instances offer discounts for committing to a specific instance type for a 1-year or 3-year term. Analyze your usage patterns to identify instances that consistently run for long periods and purchase RIs for those workloads to achieve cost savings. Monitor resource utilization. Regularly monitor your resource utilization using cloud monitoring tools. Identify instances that are underutilized and consider downsizing them to smaller instance types or consolidating them into fewer instances. More considerations for selecting and managing compute resources starts with choosing the right storage type. Different storage options come with varying performance and cost characteristics. Choose the storage type that best suits your workload needs. For example, use standard storage for frequently accessed data and archive storage for infrequently accessed data. Next, leverage managed services. Cloud providers offer managed services for various tasks like databases, machine learning, and data processing. These services often have built-in scalability and performance optimization features, relieving you of the burden of managing infrastructure. Regularly review and optimize. Cloud environments are dynamic. Your workload patterns can change over time, so it's important to regularly review your resource usage and adjust your configurations as needed. Take advantage of cost optimization reports and recommendations provided by your cloud provider to identify further cost-saving opportunities. Embrace containerization. Containerization technologies like Docker and Kubernetes allow you to package your applications and dependencies into portable units. This can improve resource utilization and make it easier to scale your applications efficiently. And utilize cloud cost management tools. Many cloud providers offer cost management tools that help you track your spending, analyze usage patterns, and identify cost-saving opportunities. Take advantage of these tools to stay within your budget and optimize your cloud cost. By implementing all these strategies, you can effectively manage your compute resources in the cloud, achieve a balance between performance and cost. Remember, it's an ongoing process that requires continuous monitoring, analysis, and adjustment to ensure optimal efficiency. Now let's take a look at some case studies. Etsy, the popular online marketplace for handmade and vintage goods, migrated to GCP to improve scalability and reduce cost. Here's how they did it. Etsy carefully analyzed its workload patterns and downsized many of its virtual machine instances to smaller and more cost-effective sizes. They also took advantage of GCP's custom machine type features, allowing them to create virtual machines with the exact combination of CPU and memory resources they needed, thus avoiding paying for excess capacity. Etsy purchased committed use discounts for their predictable workloads, locking in discounted rates for a specific period. They used preemptibility VMs for fault-tolerant workloads, taking advantage of their lower prices even though they could be interrupted. As a result, Etsy achieved significant cost savings while improving the performance and reliability of its platform. Now let's take a look at Spotify. The popular music streaming service uses GCP to deliver its massive music library to millions of users globally. To optimize cost while maintaining a high-quality user experience, Spotify implemented the following strategies. They used Spot instances to batch processing jobs and other fault-tolerant workloads, taking advantage of their lower prices. Spotify optimized its use of BigQuery, GCP's serverless data warehouse, by carefully managing query complexities and partitioning data to reduce cost. They continuously monitored their resource usage and applied data-driven insights to identify and resolve inefficiencies. As a result, Spotify was able to significantly reduce its cloud infrastructure cost while continuing to provide a seamless music streaming experience to its users. And last, we'll take a look at Khan Academy, a nonprofit organization offering free online education to millions of learners worldwide. It relies on GCP to deliver its educational content. Khan Academy employed the following strategies. They implemented auto-scaling to automatically adjust the number of instances based on demand, thus ensuring optimal performance during peak usage times, while minimizing costs during off-peak hours. Khan Academy compressed its data before storing it in GCP, significantly reducing storage cost. They used caching to store frequently accessed data in memory, reducing the need to retrieve data from slower storage systems, thus improving performance and lowering cost. As a result, they were able to scale the platform to meet the growing demand for online education, while maintaining its commitment to free access. Now let's take a look at some various strategies for monitoring and managing your cloud expenditures to keep your costs under control and avoid surprises in your bill. Your cloud provider, such as Google Cloud Platform, Amazon Web Services, or Microsoft Azure, offers built-in cost management tools. These tools provide dashboards, reports, and alerts to help you track your spending, analyze usage patterns, and identify areas where you can save money. Establish budgets for your cloud resources and set up alerts to notify you when you're approaching or exceeding your spending limits. This proactive approach prevents unexpected cost and allows you to take corrective action before it's too late. Don't pay for resources you don't need. Analyze your workload patterns and choose the right size for your instance and storage. Downsize underutilized resources and consider using auto-scaling to dynamically adjust capacity based on demand. Storage can be a significant contribution to your cloud bill. Regularly review your storage usage and delete or archive unnecessary data. Take advantage of tiered storage options, where you can store infrequently accessed data at a lower cost. Reserved instances and savings plans offer significant discounts compared to on-demand pricing in exchange for committing to a specific amount of usage over a set period. Analyze your usage patterns to identify steady-state workloads that are suitable for RIs and savings plans. Here are more strategies to monitor and manage cloud expenditures. Spot instances and preemptible VMs are significantly cheaper than on-demand instances, but can be interrupted with short notice. Use them for fault-tolerant workloads that can handle interruptions, such as batch processing jobs, testing environments, or distributed workloads. Regularly review your resource usage, cost reports, and optimization recommendations provided by your cloud provider. Make adjustments to your architecture and resource allocation to ensure you're always getting the best value for your money. These tools can provide additional features like more granular cost allocations, advanced analytics, and budgeting capabilities. Use tags to label your resources with relevant information like project, environment, or owner. This allows you to easily track costs associated with specific projects or teams, making it easier to allocate budgets and identify areas for optimization. Ensure your team members understand the cost implications of their cloud resource choices. Encourage a culture of cost awareness and optimization. Provide training on how to use cost management tools and best practices for cost-effective cloud usage. By implementing these strategies, you can effectively monitor and manage your cloud expenditures, ensuring that you get the most out of your cloud investment while keeping costs under control. Remember, cost optimization is an ongoing process, and it requires continuous attention and adjustment.
In this topic, we are going to talk about the sustained use discounts or SUDs and how they can be leveraged for cost saving. Now, when you're talking about sustained use discounts or SUDs in Google Cloud Platform, they are applied automatically and you do not have to make any kind of configurations. The only thing is that your compute engine instance must be eligible to meet this particular criteria. There are certain eligibilities that you need to have to be eligible for SUDs. Your compute instance must be running at least 25% of the entire month. Instances must be actively running for a significant portion of the billing month. It would be something like minimum at least 25%. The instance must not be preemptible. SUDs do not apply to preemptible instances, and there must not be any other discount applied on that particular instance. Your instance cannot be receiving any other discounts like committed use discounts or custom discounts, and most general purpose compute optimized, memory optimized, sole tenant, GPU enabled machine types are eligible for SUDs. Now, how does SUD work? In your compute engine, there is no option for you to configure SUD. Once you get into your compute engine, you have to ensure that your virtual machine is running at least 25% of the month. For example, you create a virtual machine but keep it on a stopped state. You are not going to get the discount. It must be running at least 25% of the month of the billing month that we are talking about. How does SUDs work? In this case, what happens is there is an automatic application. GCP automatically calculates and applies SUDs to your bill at the end of each billing cycle based on your usage throughout the month. There is a tier discount structure. The discount percentage increases incrementally with the usage of your discount. For example, if you have 25% usage, you get 2% discount. If there is 50% usage, you get 10% discount. With 75% usage, you get up to 25% discount. And with 100% usage, you can get up to 30% discount. And that is the maximum you are going to get. There are also streamlined methods of how SUDs work. There is a usage level. Now, to qualify for that discount, like I said earlier, the resource must be used for more than 25% of the month. Depending on your machine type, you can save up to 35% each month. That is when you have 100% usage. And for resource-based SUD specifically, target and apply to designated compute engine resources, and then there are no upfront commitments. You do not need to sign up or commit to a specific usage level to receive a SUD. For example, there is a committed use discount here. Now, when you're talking about committed use discount, you need to commit for a year to 3 year type of time period where you would get the committed use discount. Now, if you apply for this, then SUDs don't apply. You have to ensure that you are not using any kind of discount like custom discounts or committed use discounts. When you talk about the SUDs, is they are valuable way of saving compute engine costs without requiring any additional configuration or commitment. Once again, you don't need any specific configuration. If you go into virtual machine properties and you check out details, there are no specific features that talk about SUDs. There is nothing of that sort. It is just the virtual machine configuration. If I keep this virtual machine running for the entire month and I don't stop it, I will get up to 30% of the SUD discount. And that is about it for this particular topic. Now, in this topic, we talked about SUDs. We need to have at least 25% of the time that instance must be running. And with this, you can avail up to 2% discount. With 50% usage, you can avail 10% discount. With 75% usage, you can avail up to 20% discount. And with 100% usage, your discounts can go up to 30%. This is all done in the background, so there is no particular configuration required as we had stated earlier.
In cloud services, achieving a balance between maintaining high service levels and controlling cost is critical, yet challenging. Maintaining high service levels entails ensuring applications and services are responsive, reliable, and available to users when needed. Key factors include low latency, high throughput, and minimal downtime. Controlling cost entails optimizing resource utilization and avoiding wasteful spending. These are essential for long-term financial sustainability. Cloud resources are scalable but not infinite, requiring careful management to ensure cost efficiency. Performance testing helps to achieve this balance. It involves simulating realistic user loads and traffic patterns to assess how the system behaves under various conditions. Key aspects of performance testing includes load testing. This determines how your application performs under increasing numbers of concurrent users or requests. It identifies capacity limits and ensures the system can handle expected loads. Stress testing. Push your application beyond its expected limits to identify breaking points and potential failure modes. This will expose weaknesses and helps prepare for extreme conditions. Endurance testing. Assess your application's ability to handle sustained loads over extended periods. This will uncover issues like memory leaks and resource exhaustion that could affect long-term stability. And spike testing. Simulate sudden surges in traffic to ensure your application can gracefully handle unexpected spikes in demand. This ensures robustness under abrupt increase in load. The importance of performance testing is to identify bottlenecks. Performance testing reveals bottlenecks in code, database queries, network infrastructure, or third-party dependencies. This provides essential data for making targeted improvements. Validate scaling. Horizontal scaling adds more instances to handle increased demand. Vertical scaling enhances existing instances with more resources, thus ensuring the application can scale without sacrificing performance. Optimize resource utilization. This identifies inefficiencies, allowing for fine-tuning of resource allocation, thus ensuring resources are neither over-provisioned or under-provisioned, and ensure user satisfaction. A performant application leads to a positive user experience, higher customer satisfaction, and increased retention and revenue. Performance optimization is a continuous process that involves analyzing test results. Deep dive into performance test data to identify bottlenecks and inefficiencies. Prioritizing organizations. Focus efforts on areas that will have the most significant impact on performance and cost. Implement solutions. Refactor slow functions and eliminate unnecessary calculations. Optimize queries, add indexes, and use caching. Scale resources appropriately and configure auto-scaling policies. And monitoring and retesting. Use monitoring tools to track applications' performance in production. Repeat performance tests to ensure optimizations are effective and to catch new issues early. Balancing performance and cost often involve trade-offs. For example, using larger and more powerful cloud instances can significantly improve performance but also increase cost. Choosing smaller, less powerful instances may be more cost-effective, but could lead to performance limitations under heavy loads. Implementing caching can drastically improve response times and reduce the load on back-end resources, but it also introduces additional costs for storage and management of cache. Utilizing a CDN can enhance performance by distributing content closer to users, but it also incurs costs for data transfers and storage across multiple geographical locations. The key is to find the optimal balance where performance meets acceptable levels without incurring excessive cost. This involves carefully weighing the potential benefits of each optimization against its associated cost and making informed decisions based on your specific requirements and budget. Now let's take a look at tools and techniques for optimization. Cloud monitoring. Collect data on application performance, resource utilization, and error rates. Cloud Profiler and Cloud Trace. Identify specific functions and code paths that cause performance bottlenecks. Follow requests through the system to pinpoint latency sources. Caching. Implement caching to store frequently accessed data in memory, reducing load times. Load balancing. Spread incoming traffic across multiple instances to prevent overload. And auto-scaling. Configure policies to automatically adjust the number of instances based on demand. Now let's summarize what we have covered. We took a look at cloud service performance using Google Cloud's Operations Suite, application of Cloud Trace and Cloud Profiler, and preemptible VMs. Committed use discounts, process for configuring and using cloud monitoring, and strategies for sizing and scaling resource implementation of network tiers. Implementation of network tiers, application of cloud functions and GKE, and considerations for selecting and managing compute resources. Case studies on cost optimization strategies. Strategies for monitoring and managing cloud expenditures and sustained use discounts. And role of performance testing and optimization in maintaining high service levels. Coming up next, we'll take a look at managing and securing service accounts. Welcome to Managing and Securing Service Accounts. I'm Ron Johnson. In this course, we will take a look at defining the role and importance of service accounts in Google Cloud Platform, describe the process of creating and managing service accounts for various GCP services, explain the best practices for assigning IAM roles to service accounts to ensure principle of least privilege, outline the steps for securely managing keys associated with service accounts, describe how to audit service account usage and access permissions using cloud audit logs, rotate and manage service account keys to enhance security, identify strategies for minimizing the use of service accounts with broad permissions, analyze case studies illustrating the effect use of service accounts in complex GCP environments, analyze the impact of service account misconfiguration on security and how to mitigate these risks, compare the use of service accounts versus user accounts for automated tasks within GCP, illustrate the integration of service accounts with GCP Cloud Build for CI/CD pipelines, and describe the considerations for service account usage in multi-cloud and hybrid cloud architecture. Service accounts are a special type of Google accounts that are not associated with a specific user or person. Instead, they are designed to represent applications or virtual machines running on GCP. Think of a service account as an identity for your application. When your application needs access to GCP resources, it uses the service account credentials to authenticate itself and prove that it has the necessary permissions. You can create service accounts through the GCP console, the Cloud Command Line tool, or programmatically using an IAM API. Each service account has a unique email address that serves as its identifier. Service accounts play a crucial role in GCP security and resource management. Here are some key reasons why they are important. By using service accounts, you can grant your application the precise permissions they need to access specific GCP resources. This follows the principle of least privilege, reducing the risk of unauthorized access or misuse. Service accounts enable you to automate tasks and processes on GCP. For example, you can create a service account that automatically backs up your data to cloud storage, or sends notifications when certain events occur. GCP logs the actions performed by the service account, making it easier to track activity and identify any security or compliance issues. Now here's some best practices for service accounts. Grant service accounts only the minimum permissions they need to perform their task. To control what a service account can do, you assign it one or more roles. Roles are a collection of permissions that grant access to specific GCP resources and actions. For example, you might assign the storage object admin role to a service account that needs to manage files in cloud storage. Regularly rotate the credentials of your service accounts to reduce the risk of unauthorized access. And keep an eye on the activity of your service accounts to detect any unusual or unauthorized behavior. Now let's take a look at how to create a service account in Google Cloud. First, log into your Google Cloud console. From the navigation menu, go to IAM and Admin, and then select Service Account. Click on the Create Service Account button. You'll be asked to provide a name for your service account. And last, you will click on Create and Continue. There are two options. You can choose to grant your service account specific permissions right away. These permissions are defined by IAM roles. For example, Storage Object Viewer. If you're not sure which role to assign yet, you can skip this step and come back to it later. Another option would be Generate Key. If your application needs to access GCP resources outside of Google's environment, you'll need to create a key for your service account. This key will be a JSON file containing the credentials that your application will use to authenticate itself. If your application runs within GCP, you usually don't need to create a key. Once created, click Done. Now you have your service account. Some steps to managing the service account. Granting additional permissions. If you don't assign permissions when creating the service account, or if you need to modify them later, you can easily do so. Go to the IAM section in the Google Cloud Console, find your service account, and click on the Edit Principal button to add and remove roles. Rotate keys. For security purposes, it's a good practice to rotate the keys of your service account periodically. This means generating new keys and deleting the old ones. This helps to mitigate the risk of unauthorized access in case a key gets compromised. Monitoring activity. GCP logs all the actions performed by the service account. Regularly review the logs to ensure that your service accounts are being used as intended and detect any unauthorized activity. Deleting service accounts. If you no longer need a service account, you can delete it from the Google Cloud Console. This will revoke all the permissions associated with the service account and make it unusable. Some important concepts to consider when managing keys. Once again, grant additional permissions. If you don't assign permissions when creating the service account, or if you need to modify them later, you can easily do so. Have a rotating key schedule. For security purposes, it's good practice to rotate the keys of your service account periodically. This means generating new keys and deleting the old ones. And last, constantly monitor your actual keys. GCP logs all the actions performed by service accounts. Regularly review the logs to ensure that your service accounts are being used as intended. Once again, if you no longer need a service account, you can delete it from your Google Cloud Console. Let's break down the best practices for assigning IAM roles to service accounts in the Google Cloud Platform. First, understand the service account's purpose. Before assigning any roles, clearly define the specific task and actions the service account needs to perform. This could be accessing storage buckets, running virtual machines, or interacting with specific APIs. Knowing the service account's purpose helps to determine the exact permissions it requires. Start with the minimum required permissions. Begin by assigning only the essential roles that are absolutely necessary for the service account to fulfill its task. Avoid granting broad permissions or roles that encompass actions the service account doesn't need. Use fine-grained permissions. GCP offers a wide range of granular IAM roles that grant access to specific resources and actions. Use these fine-grained roles whenever possible to avoid granting excessive permissions. For example, instead of granting the storage admin role, which allows full control over all storage buckets, you might assign the storage object viewer role if the service account only needs to read objects from a bucket. Regularly review and revoke permissions. Periodically review the roles assigned to your service accounts and revoke any permissions that are no longer needed. As your application evolves or changes, its permission requirements may also change. Ensure that the service account permissions stay aligned with its current responsibilities. Use custom roles if necessary. If the predefined IAM role doesn't precisely match your service account's needs, create custom roles. Custom roles allows you to tailor the permissions to exactly what your service accounts requires, further adhering to principles of least privilege. Avoid using default service accounts. Each GCP project has default service accounts, like the Compute Engine default service account. Avoid using these default accounts for your applications. Instead, create dedicated service accounts for each application or service with tailored permissions. Monitor service account activity. Keep a close eye on the activity of your service account using cloud logging or other monitoring tools. This helps you detect any unusual or unauthorized behavior and promptly adjust permissions if needed. Automate permission management if possible. If you have a large number of service accounts or permission needs to be changed frequently, consider automating the permission management process using tools like Terraform or the GCP IAM API. This can help you consistently enforce least privilege policies and reduce the risk of human error. By adhering to these best practices, you can significantly enhance the security of your GCP environment. By granting these service accounts only the permissions they absolutely need, you minimize the potential attack surface and reduce the risk of unauthorized access to your valuable cloud resources. Now let's outline the steps for securely managing keys associated with service accounts in Google Cloud Platform. Minimize key creation. Don't create keys unnecessarily. Often, service accounts can access GCP resources without needing a separate key file. If possible, use alternative authentication methods like Workload Identity Federation or the GCP Metadata Server. Grant key creation permissions cautiously. Limit the number of users or service accounts that have permissions to create keys. Only those who absolutely need to create keys should be granted the necessary IAM roles. Store keys securely. Never store service account keys directly on a computer's file system or in a source code repository. Instead, use a secure key management system like HashiCorp Vault, Google Cloud Secret Manager, or Hardware Security Module. Rotate keys regularly. Establish a schedule for rotating your service account keys. This means creating new keys and deleting the old ones at a regular interval, for example, every 90 days. Rotating keys reduce the risk of unauthorized access if a key gets compromised. Set expiration dates. When creating keys, set expiration dates for the keys. This ensures that keys automatically expire after certain periods, limiting the window of opportunity for unauthorized access if a key is leaked. Monitor key usage. Keep track of who is using your service account keys and for what purpose. GCP logs activity related to service accounts, allowing you to identify any unusual or unauthorized behavior. Other areas of securely managing keys include revoking compromised keys immediately. If you suspect that a service account key has been compromised, revoke it immediately. This prevents unauthorized access and minimizes potential damage. Disable key creation for specific projects. If a project doesn't require service account keys, use organization policy constraints to disable key creation for that project. This adds an extra layer of security by preventing users from accidentally or intentionally creating keys when they're not needed. Use short-lived credentials. Whenever possible, use short-lived credentials instead of long-term keys. Short-lived credentials expire after a short period, reducing the risk of unauthorized access. And finally, limit access to the metadata server. The GCP Metadata Server provides information about running instances, including service account credentials. Ensure that only authorized applications and services can access the metadata server to prevent unauthorized access to credentials. By following these best practices, You can significantly enhance the security of your service account keys and protect your GCP resources from unauthorized access. Remember, key management is an ongoing process, and it's essential to stay vigilant and adapt your security practices as needed. Cloud audit logs are a treasure trove of information, recording every action taken on your GCP resources, including those by service accounts. They capture who did what, when they did it, and which resource was affected. In the Cloud Logging console, you can filter the logs specifically for service account activity. This lets you see a focused view of everything that your service accounts are doing. Cloud audit logs detail which specific permissions were used by the service account for each action. By scrutinizing these details, you can verify that your service accounts are only using the permissions they should and not accessing resources they shouldn't. Cloud audit logs can act as your early warning system. If you see unexpected activity, like a service account accessing a resource it's not supposed to, this could indicate a security breach. You can investigate and take action promptly. Sometimes a service account might have more permissions than it actually needs. This is called overprivileged. By reviewing cloud audit logs, you can identify any permissions that are not being used and remove them. This helps to minimize your security risk. If a service account has not been used for a while, it might be a good candidate for deletion. Inactive accounts can become a security risk if their credentials are compromised. You can export cloud audit logs to other GCP services like BigQuery for more advanced analysis. This allows you to run complex queries, create custom reports, and gain deeper insight into service account behavior. Create alerts in cloud monitoring to notify you of any unusual or potential risky activity by your service account. This helps you stay on top of any security threats and gives you the ability to respond quickly. Make auditing service account usage and permissions a regular practice. This will help you ensure that your GCP environment remains secure and that your service accounts are not being misused.
In this topic, we'll talk about the process for rotating and managing service account keys to enhance security. Now, there are two ways you can do this. One is you can create keys with the service account. If I just click on SKS-Cloud Build, if I go into the service account, there is a tab called Keys. I can create keys and use method like scripting to rotate these keys for an application. That is one way. For example, I can simply go ahead and say create new key, and I will go ahead and create this key by clicking create. And now this is basically JSON type. Now this key is now downloaded onto my system. Once this key is created, I need to go ahead and create new key, and then it creates another key for me. Now I have two keys. What I need to do is I need to rotate them, and then this can be manually done, or this can be done through an automated method like a script that can rotate these keys for me. And I need to ensure that once the second key is in place as the root, and then I need to disable the first one so that it cannot be misused. Now another method is basically what I can do is I can go to Cloud Key Management and I can create a keyring. You cannot directly import service account keys into Cloud KMS keyring. There are different methods that you can use to manage service account keys more securely with KMS. Now you can encrypt service account keys with Cloud KMS. You can generate your service account keys, for example, in the JSON format. You can use the Cloud KMS to encrypt JSON keys with a symmetric encryption key, and then you can store the encrypted key in a location like Cloud Storage Bucket. Now the benefit that you get is that there is enhanced security which helps you protect the private key material from unauthorized access, and there is credential management which consolidates key management in Cloud KMS. And then you can use Cloud KMS to generate and manage encryption keys for your application. With this method, you can use this particular keyring and you can generate keys, and then you can basically assign permissions to the service account so that these keys can be used. For example, if I just go ahead and click create keyring, I define a keyring name. For example, I just say SKS-key-ring5, and I can select whether it is regional or it is multi-regional or global. Set the region, which I say US Central 1, and then I go ahead and create. Now the keyring is created, but it does not have any keys with it. You need to create keys. It automatically takes you to the particular screen. Now here I just say SKS-key-5A, and I need to select the protection level. Let's say we just go ahead with the default value of software. We can click continue and then generate key or import key. So if I just say generated key, then it tells me which type of key do you want to generate. It is going to be symmetric, encrypt, decrypt. I just leave that and click continue. You need to set the rotation period. Now, if I say rotation is for 30 days, and I can go ahead and click continue now. This is now basically creating a keyring with the rotation of keys. This particular key is created, and if I go back to the keyring that we had just created one, we need to obviously create another one and click on SKS keyring 5, and here then there is this key which is SKS-key-5A, and it gives us the overview. For example, key rotation frequency. We had set it up to 30, and then it is the Google symmetric key, and purpose is encrypt and decrypt information. I can simply go ahead and create another key. For example, let's go ahead and just do that right away. And I'm going to just say 5A. Instead of that, I'm going to name it as SKS-key-5B. And the rest, we just keep everything here and click continue. Click continue once again. And here we can change the rotation time to 30. And I'm going to go ahead and click create now. This is now done. We have created this symmetry key, or even if you have created asymmetric keys, you can use these keys within your application to encrypt sensitive data or sign token, and then you need to grant service accounts the permission to access these keys in KMS. What happens is then there are certain benefits you get. There is separation of concern, which means your application does not need to store the encryption keys directly. And secondly, there is a centralized key management. You are leveraging KMS for key rotation, versioning, and access control. Now, obviously with that, there is a drawback also, which means you require modifying your application code to integrate with cloud KMS. That's all for this particular topic. Now, just to quickly recap, in this particular topic, we looked at how to create keys within cloud KMS. We also looked at how to create keys in the service account properties. Once you have done that, you can either manually rotate, or you can use a script to rotate the service account keys, or you can use something like Cloud KMS to create a keyring. Create keys within that, and then you can set them for automatic rotation for certain days. And in our case, we set it up for 30 days.
Let's take a look at strategies for minimizing the use of service accounts. Grant service accounts only the permissions they absolutely need to perform their specific task. Avoid assigning broad roles like editor or owner, which give wide-ranging access to your resources. Instead, opt for more granular roles that are tailored to the specific actions the service account needs to perform. If a service account needs to perform multiple tasks, break them down into smaller, more specific roles. For example, instead of granting the storage admin role, which allows full control over all storage buckets, create separate roles for storage object creator, storage object viewer, and storage object deleter. If the predefined IAM role in GCP are too broad for your needs, create custom roles. Custom roles allow you to define very specific permissions, giving you precise control over what a service account can and cannot do. Periodically review the permissions granted to your service account. As your applications and services evolve, their permissions requirements may change. Revoke any permissions that are no longer necessary to reduce the potential impact of a security breach. Workload Identity Federation allows you to assign identities from your existing identity provider, like Active Directory or Okta, to workloads running on GCP. Instead of using long-lived service account keys, consider using short-lived credentials that expire after a limited time. This can be done using OAuthentication 2.0 tokens or OpenID Connect tokens. Short-lived credentials provide an extra layer of security by minimizing the window of opportunity for unauthorized access. Keep a close watch on the activities of your service account using cloud audit logs. Look for any unusual or unexpected actions that indicate a security breach or misconfigured permissions. Set up alerts to notify you of any suspicious activity. If you have a large number of service accounts or if permissions need to change frequently, consider automating the permission management process using tools like Terraform or the GCP IAM API. This can help ensure consistency and reduce the risk of human error. Now let's take a look at some case studies. A major data analytic company was processing petabytes of data using Apache Spark on Google Dataproc. They needed a way to securely access and manage data stored in the cloud storage while maintaining fine-grained control over permissions. Their solution was the company created separate service accounts for different stages of their data processing pipeline. Each service account was granted specific roles and permissions based on the task it needed to perform. For example, one service account was responsible for reading data from cloud storage, while another was responsible for writing the processed data back to cloud storage. This approach ensured that each service account had only the minimum necessary permissions, reducing the risk of accidental or malicious actions. The second case study entails an automated infrastructure deployment. A rapidly growing software-as-a-service company needed to automate the deployment and management of their infrastructure on GCP. They wanted to ensure that their deployment scripts had the necessary permissions to create and modify resources without compromising security. In their solution, the company created a dedicated service account for the deployment scripts. They granted the service account the specific roles required for infrastructure deployment, such as compute instance admin and storage admin. This allowed the scripts to automatically provision and configure resources without requiring manual intervention. To further enhance security, they rotated the service account credentials regularly and implemented strict access controls to limit who could modify and deploy the scripts. Let's break down the impact of service account misconfiguration on security in Google Cloud Platform and discuss how to mitigate those risks. Incorrectly configured service accounts can grant unintended access to sensitive data and resources. For example, a service account with excessive permissions could allow unauthorized users or applications to read, modify, or delete data that they shouldn't have access to. This can lead to breached data, service disruptions, and financial losses. A misconfigured service account with powerful privileges, like the owner role, could be exploited by attackers to gain even more access and control over your GCP environment. This could lead to the compromise of sensitive data, the installation of malware, or even the complete takeover of your infrastructure. If a service account has access to sensitive data but lacks proper security controls, an attacker could use it to exfiltrate data from your GCP environment. This could involve copying data to unauthorized locations or transmitting it to external servers without your knowledge. Misconfigured service accounts can also lead to resource abuse. For example, a service account with excessive permissions could launch a large number of virtual machines, consuming your resource and driving up your cost. Many industries have strict regulations regarding data security and privacy. Misconfigured service accounts could result in compliance violations, leading to fines, legal actions, and reputational damage. Now let's take a look at some mitigation strategies as it relates to service account misconfiguration. Grant service accounts only the minimum permissions they need to perform their task. Avoid using overly broad roles like owner or editor. You should always educate your team members about the importance of service account security and the potential risk of misconfigurations. Ensure they understand the principle of least privilege and the proper procedures for creating and managing service accounts. Regularly review the permissions assigned to your service accounts and revoke any permissions that are no longer needed. Rotate the keys of your service account at regular intervals to reduce the risk of unauthorized access in case a key is compromised. Set up alerts to notify you of any unusual or suspicious activity related to your service accounts. This helps you detect potential security breaches early on. Consider using automated tools to make your service accounts and their permissions. These tools can help you enforce consistent security policies and reduce the risk of human error. And finally, have a clear incident response plan in place to deal with any security breaches or unauthorized access attempts. This plan should outline the steps to take to contain the damage, identify the root cause, and prevent future incidents. As covered in Course 3, this comparison highlights the key differences between service accounts and normal user accounts in GCP, emphasizing their respective purposes, authentication methods, mode of interaction, permission management, and lifecycle management. The purpose of a service account is to represent applications or services that require programmatic access to GCP resources. The purpose of a normal user account is to represent human users who interact with GCP resources through web consoles, command line interfaces, or other user interfaces. Service accounts primarily use key pairs or OAuth 2.0 tokens for authentication, allowing automated processes to authenticate without human intervention. Normal user accounts typically authenticated using a username password combination, along with additional security measures such as two-factor authentication. Service accounts interact programmatically with GCP resources via API calls, software development kits, or other automated tools. Normal user accounts interact with GCP resources through web consoles, CLI tools, or other user interfaces that require manual input and interaction. Service accounts provide more granular control over individual actions, allowing fine-tuning of permissions for specific tasks or workflows. Normal user accounts often has broader permissions tied to job roles or responsibilities, granting access to a wider range of GCP resources and services. Service accounts are created and deleted as needed to support automation and application requirements. Its lifecycle is typically managed programmatically. Normal user accounts are managed by IT administrators or the users themselves, and its lifecycle may be tied to organizational policies, employee status, or user preferences. Let's take a look at use cases of a service account. Service accounts are commonly used with Compute Engine Instance to grant them access to other GCP services, such as cloud storage or BigQuery, for tasks like reading, writing, or processing data. When creating a Compute Engine instance, you can specify a service account to associate with the instance. This service account acts as the identity for the instance when it interacts with other GCP services. By assigning appropriate roles and permissions to this service account, you can control the level of access granted to the Compute Engine instance, ensuring that it can perform its intended task securely and efficiently. Service accounts play a crucial role in enabling cloud functions to trigger other GCP services, or manipulating data within the project. Each function is associated with a service account, which determines the permissions available to the function when it interacts with other GCP resources. By configuring the appropriate roles and permissions for the service account associated with a cloud function, you can ensure that it has the necessary access to perform its designated actions, such as reading from or writing to cloud storage, invoking other cloud functions, or interacting with databases like BigQuery. Service accounts can be used to authorize custom applications running outside of GCP to securely access and interact with GCP resources. To integrate a custom application with GCP services, you can create a service account and generate a set of credentials, such as a JSON key file, OAuth 2.0 access token, which the application can use to authenticate itself to a GCP API. By assigning appropriate roles and permissions to the service account associated with the custom application, you can control the scope of actions it can perform within GCP, ensuring that it adheres to the principles of least privilege and only accesses the resources necessary for its functionality. Service accounts are integral to enabling automated data processing workflows in GCP, allowing data pipelines to transfer and transform data between GCP services seamlessly. In data processing workflows, service accounts are used to authenticate and authorize the various components involved in the pipeline, such as data ingestion tools, data processing frameworks, and storage services. By granting appropriate roles and permissions to the service accounts associated with each component, you can orchestrate complex data processing tasks securely, ensuring that sensitive data is accessed and processed only by authorized entities. Service accounts are instrumental in automating build and deployment processes within CI/CD pipelines by granting them access to the necessary GCP resources. In CI/CD pipelines, service accounts are used to authenticate and authorize the CI/CD tools, such as Jenkins, GitLab CI/CD, or Cloud Build, to interact with GCP services for tasks like building container images, deploying applications, or running tests. By configuring the appropriate roles and permissions for the service accounts associated with the CI/CD tools, you can ensure that they have the required access to perform their designated actions securely and efficiently, facilitating streamlines and automated software delivery processes.
In this topic, we'll learn how to integrate a service account with GCP's Cloud Build for CI/CD pipeline. What it means is when you're creating a build, you can associate a service account with that. And obviously, that service account needs to have certain level of permissions and privileges for you to be able to use that service account. And we will talk about that in just a moment. Now, what are service accounts? They are special types of Google accounts designed to represent non-human users such as applications, virtual machines, or any other services on GCP. They are not meant to be used by people directly. Some of the key features of service accounts is that they can act as an identity for your applications or services, therefore allowing them to interact with GCP APIs and resources. They're also used to authenticate and authorize within your GCP project. Each service account has an email address which is unique and it basically identifies the service account itself. If I just hop over my service accounts page in IAM and admin, now notice this is that there is a service account which is SKS-cloud build and at the rate, then this is your project name which is SKS001 and then the default suffix is iam.gsserviceaccount.com. Now, this is standardized suffix for all the service accounts. If you are using these service accounts within the same project, then you will have the same suffix starting from at the rate and anything before that, which is the name of your service account. Now, to be able to create a service account, you need to just come to IAM and admin and visit service accounts tab and then you can click here to create a service account. It is a very basic process. And now when you have a cloud build pipeline that you are going to create, then what you need to do is you need to basically go ahead and come to triggers. Now I already have a series of triggers that I have created. For example, there is a feature dash trigger. There is first app dash one, Jenkins triggered build and SKS build. Now, if I click on this first app, it should not have any service account associated. If I scroll down, service account is none. Now, whatever service account that I had created in IAM, they'll all be listed here. For example, SKS-cloud build. Now, if I go over to service accounts, there should be SKS-cloud build. For me to be able to do that, we need to ensure that the service account is used appropriately. We need to have a specific set of privileges that are going to be needed. For example, it might be just to generate the build or whatever the purpose of that particular service account is. You need to assign those privileges here. If I come to SKS-cloud build, click on this and we can see whether it has any kind of privileges or not. Now, if I go to the permission tab here, it does not have any kind of permissions assigned. So I can grant access to this particular service account. Now, We need to just ensure that whatever permissions we are going to assign or the privileges we are going to be assigning to this particular service account, we are following the principle of least privilege. We should not assign excessive permissions to a service account. Remember, it is a non-human account which is going to be associated with applications or any other services that you are running in GCP. Therefore, it is always advisable and it is the best practice to assign the bare minimum level of privileges that is needed for the service account to work with. That's all. That's all you need. Now, if I go back to edit trigger, I can, for example, just select SKS-cloud build, and that's all I need to do. I can simply go ahead and save, and the process is still the same. When you are creating a new trigger, you need to define the name, the region, push to branch, first gen or second gen. Then you need to assign a repository from GitHub. Whether you want to use the cloud build.yml file or you want to write inline, that is up to you. If I just click on open editor, this is the basic code that I have, which just flashes hello world, and then I just come down here. If my service account is not listed here, that means it is not mapped to this particular build. So I need to go ahead and create a service account here. And if it is not created, I would need to create the service account and then come back. It should be listed here, and then I just select this and go ahead and save it. That is all is needed to be performed to integrate a service account within a pipeline. Now, just to quickly recap in this particular topic, we talked about the service accounts in IAM and admin, and then we need to navigate to the service account tabs in the left pane, and then we talked about the kind of privileges you should have on that particular service account. Basically, you need to practice the principle of least privilege, and then when you are creating a trigger, you simply select the particular service account that you have created and save the trigger. That's it. This is all you have to do to integrate a service account within a build pipeline.
Let's discuss the consideration for using service accounts in multiple cloud and hybrid cloud architecture. Service accounts are primarily designed for a single cloud provider. In multi-cloud and hybrid scenarios, managing multiple service accounts for different platforms can be cumbersome. Identity federation allows you to establish a trust relationship between your cloud providers, enabling you to use a single identity across multiple platforms. This simplifies authentication and authorization, reducing the overhead of managing multiple service accounts. Each cloud provider has its own set of permissions and roles for service accounts. When working with multiple platforms, it's important to map the permissions correctly to ensure consistent access control across your environment. This involves understanding the equivalent roles and permissions across different providers and ensuring that the service accounts have the appropriate access levels. Managing service account credentials across multiple clouds can be a security challenge. It's crucial to securely store and rotate credentials to minimize the risk of compromise. Consider using a centralized secret management solution or a cloud-agnostic identity management platform to streamline credential management and enhance security. In a multi-cloud or hybrid environment, it's essential to have centralized monitoring and auditing in place to track the activity of service accounts across all platforms. This helps you detect any unauthorized access, suspicious behavior, or misconfiguration that could compromise your security. Ensure that you have secure mechanisms in place for cross-cloud communications, such as using virtual private networks or dedicated interconnects. Some other considerations include security policies and governance. Establish consistent security policies and governance for service accounts across all cloud providers. This includes defining clear roles and responsibilities for managing service accounts, enforcing the principle of least privilege, and implementing regular audits and reviews. Each cloud provider may have specific requirements or limitations regarding service accounts. Be sure to familiarize yourself with the specific guidelines and best practices for each platform you're using. This might include specific authentication mechanisms, supported identity providers for federation, or restrictions on cross-cloud access. Consider using automation and orchestration tools to manage service accounts across multiple cloud environments. These tools can help you streamline provisioning, deprovisioning, and permission management, reducing the risk of human error and ensuring consistent security policies. And in a multi-cloud or hybrid architecture, it's important to have a comprehensive disaster recovery and business continuity plan. This should include provisions for managing service accounts in the event of a failure or outage. This might invoke replicating service accounts across different regions or availability zones, or having backup credentials stored in a secure location. Now let's summarize what we have covered. We took a look at role and importance of service accounts, creating and managing service accounts, and best practices for assigning IAM roles, steps for securely managing keys, service accounts, and access permission auditing using cloud audit logs, and rotating and managing service account keys, minimizing the use of service accounts, service account case studies, and risk mitigations during service account misconfigurations. Service accounts versus user accounts, and integration of service accounts with cloud build. Considerations for service account use in multi-cloud and hybrid cloud. Coming up next, we'll take a look at implementing network security and policies.